So, good afternoon, everybody here from Portugal, and we are now about to resume and start the second session of the day. I'm sharing in replacing Alexei, which has not been able to join us. Let us hope that he will be able to do so as soon as possible, either still today as a participant or then tomorrow. And today's first talk is by David Wans, whom I salute, and it's very nice to see you. From time to time, we just go along the same road, or at least one conference or another, and David is going to talk to us about primordial black holes from stochastic inflation. So up to you, David.
Thank you very much, Paolo, and I'm very pleased to be able to connect with you all, at least online, virtually today, and I hope we'll be able to get back to meeting together in person soon. It feels like that will be possible again soon, so we look forward to that. Today, I'd like to talk about some work I've been doing recently, in fact, in recent years, with my colleagues in Portsmouth, Paris, and elsewhere on primordial black holes, the generation of primordial black holes from stochastic inflation. And I'm lucky enough to we've had two excellent talks this morning, which introduced both primordial black holes and inflation, and indeed perturbations from inflation in the very early universe, from Professors Starobinsky and Dolgov. So I can launch straight into the topic there. So as I say, this is work with colleagues in Portsmouth, in particular two PhD students, Joe Jackson and Chris Patterson, who graduated just last year, my colleagues Husha Asadulahi and Kazuya Koyama, and collaborating with Vincent Benin in Paris. Vincent indeed has pioneered a lot of the techniques and studies that I'll be giving some details from today. So let me start briefly reviewing the idea of primordial black holes. In truth, I'm not really going to say that much about primordial black holes, but I'm going to use them as a motivation for studying large density fluctuations originating from inflation in the early universe. And there is this fascinating idea that's been around since the pioneering work in the 60s and 70s, that if there were very large density perturbations in the early universe, so when the density contrast delta here would exceed some critical value of order unity in the early radiation-dominated universe, then these large density perturbations could collapse under their own gravity, form black holes, and these might survive until the present day and be detectable perhaps in our universe today. And an interesting feature of this scenario, indeed, when you think about it, it's really a feature of early universe cosmology, is that cosmology spans a great range of scales. And so the masses of the primordial black holes that you could form at different times in the hot radiation-dominated early universe themselves could span a wide range of scales. And the idea is that these black holes would form as density perturbations come inside the horizon in the early universe. And so naturally, the mass of the black hole formed would be related to the horizon mass at the time. And indeed, you could form solar mass black holes when the time t here was 1 microsecond after the hot Big Bang. But you could indeed form much larger black holes later in the radiation-dominated universe, or much lighter black holes at early times. So this is sort of illustrated here in a cartoon of a schematic diagram I've picked up from this recent review, where the idea here is that you have a couple of density perturbations. Indeed, these are large primordial density perturbations with wavelengths lambda 1 or lambda 2, and at very early times they're much larger than the horizon size CT, but the horizon size grows. And so although they don't form black holes when these perturbations are much larger than the horizon, as the horizon size grows and first of all becomes larger than lambda1, forming a black hole with mass related to the horizon size at this time, then the horizon size grows again. That is, the cosmological horizon size is growing again. And so at a later time, once it's larger than this second wavelength lambda2, you start forming, have the possibility to form primordial black holes from these longer wavelength perturbations. And so you get larger masses associated with the formation of black holes at later times. And as I say, in principle, this could form black holes across a wide range of scales. And one can then consider what the effect this would have in the universe today. And there's been a lot of interest in this, as I said, renewed interest in recent years in this, in considering and reanalyzing some of these constraints on the allowed abundance of black holes. Partly because people are interested in taking more seriously perhaps these as potential dark matter candidates. We know there are constraints from other astrophysical events, for instance, microlensing by these as black holes as compact objects in the universe today. Other dynamical effects of having large dark matter, black holes as dark matter, or indeed evaporation and ultimately explosion of very light dark matter, very light primordial black holes. So there are potentially windows where these black holes could form, still be the dominant contribution to dark matter in the universe today. Or even if they're subdominant as a contribution to dark matter, the total dark matter density in the universe today, they could have interesting astrophysical signatures. As Professor Dolgoff was saying, these could potentially provide the origin of some or all of the events seen by the LIGO-Virgo gravitational wave detectors. If these are, if the black holes that we see, the binary black hole mergers we see come from primordial black holes. So this in particular, the fact that we now observe black hole merger events directly has renewed interest in the possible primordial origin of these events. But even if they're playing an important role in the universe today and some significant fraction of the dark matter perhaps in the universe today, it's worth remembering that the mass fraction, the fraction of the universe going into the formation of black holes when they form in the very early universe has to be much smaller. So if they're of order the solar mass black holes as seen by LIGO-Virgo events, then the abundance would have to be less by a factor of about 10 to the 8 at the time of formation of these black holes. So these would be very rare events, necessarily very rare events in the early universe when they formed, and indeed that's this mass fraction abundance could be very much orders of magnitude smaller for some of these very light primordial black hole candidates. So this is the motivation for studying mechanisms for the origin of black holes. And in particular, I'm going to consider whether these could form from inflation in the very early universe. You might wonder how all of this can be compatible with the view of the early universe that we see. Our best picture of the early universe really comes from observations of the cosmic microwave background sky. If this is a snapshot of the primordial plasma 300,000–400,000 years after the hot Big Bang, then at that time, the typical fluctuations, the fluctuations we see in the cosmic microwave background sky are at about 1 part in 100,000. So this is a very smooth universe where the density fluctuations giving rise to these temperature fluctuations, which indeed I'll characterize the amplitude of the primordial perturbations in scalar perturbations in terms of this zeta variable, which you can think of as the dimensionless density perturbation. Well, on the larger scales in the CMB, you can relate this directly to the temperature fluctuation. As Alexei Starobinsky said, delta T over T in the CMB sky on the large scales is about 1/5 of zeta. So we know zeta, the typical fluctuations we're seeing here, what are large scales in the universe today, are very small. So we have a very orderly view of the early universe. And indeed, if this comes from inflation, then we have a very calm, orderly view of inflation in the early universe, where density fluctuations here are like ripples, very gentle ripples on the surface of the lake here. If we're looking at primordial black holes, on the other hand, they would form from large density perturbations in the early universe, in the radiation era. So if we work in terms of zeta, then we can construct from that a smoothed density contrast, or sometimes called the compaction function, on a given scale R. This is derived from zeta and its derivatives. And these black holes would form when this smooth density contrast exceeds a critical value. And as I say, this would have to be can only be a small fraction of the universe going into these large fluctuations to form black holes. So if typically one uses thinks of primordial density fluctuations being described by a Gaussian distribution, then we're looking way down into the tail of this distribution at where the density perturbations are just suppressed by factors of 10 to the -8 or smaller in terms of the abundance, but also where these are correspond to large density fluctuations coming from large values of the primordial curvature perturbation zeta. So I'll argue that in fact this assumption that the primordial density perturbations, the probability distribution function for these density perturbations is a Gaussian all the way out into the tail of the distribution is in fact not well justified in many cases, and that when we look out into these extreme fluctuations, eventually in the tail of the distribution we find very large deviations from Gaussianity. So what we're thinking about here, if I think of an image for what the fluctuations that we're interested in look like, it's not so much ripples on the surface of the lake, it's some great wave disturbing the surface of the sea here. Very large so we need a non-perturbative approach to calculate these large rare excursions, some great wave in the primordial density field. So that's the dramatic image I have in mind of the fluctuations that we are studying in this case. Very different from the typical small fluctuations that we study in the perturbative approach. Okay, so let's see though how we actually model these. First of all, starting from that orderly classical background during inflation. So I'm just going to be thinking here in terms of the simplest single field, scalar field driven models of inflation, a minimally coupled canonical scalar field. But if it has a self-interaction potential energy that dominates the expansion, dominates the energy density. So in particular, if the potential energy is much larger than the kinetic energy of the field, then we know we can have an almost constant Hubble expansion rate. So that is a Hubble expansion rate that changes slowly. So there's a small change on a Hubble time. So this first slow roll parameter epsilon here, h dot over h squared, is much less than 1. So that's consistent with the idea that kinetic energy is much less than the potential energy that's driving the Hubble expansion rate h. So this is the classical background is indeed entirely homogeneous and uniform, spatially uniform, just time dependent. And then this inflates the universe. We measure the amount of expansion in terms of the number of e-folds n, as introduced by Alexei Starobinsky this morning. So n is just the integral of that Hubble expansion over time. So this gives us the logarithm of the scale factor. And we can turn this in the single field model, we can simply turn this into an integral over the scalar field, h over phi dot d phi. And the fluctuations zeta that I've been talking about, the density primordial metric perturbations that give rise to the density fluctuations in the early universe, as Alexei described, is just the fluctuations with respect to the average expansion. So zeta is delta n here. And you can see from this expression for n in the background cosmology that we can interpret zeta as being coming from a perturbation in the field relative to the classical evolution. So in fact, this zeta here can be thought of as the ratio between the quantum fluctuations in the scalar field on small scales relative to the homogeneous background, the classical evolution, h to the -1 phi dot. The delta phi classical is the change in phi in a Hubble time from the classical drift. So the picture here is as the field classically would roll down its potential to the minimum of the energy density, we have on top of that small quantum fluctuations, and these give rise to a perturbation in the local expansion history up until the point where the field reaches the end of inflation. And this will give us a metric perturbation in the universe at the end of inflation, at the beginning of the radiation-dominated era. And in the typical picture, so as I say, what we have here is that the fluctuations here are basically the ratio of the quantum to classical the quantum perturbations to the classical drift during inflation. And in the standard perturbative approach, this must be small. And indeed, for typical fluctuations in the CMB sky, 1 part in 10 to the 5, this would appear to offer a good description. But if we're looking at primordial black holes, then we must be looking up in a regime where this zeta becomes large. And if zeta becomes of order unity, then you're looking at a regime where the quantum fluctuations are no longer small compared to the classical. We're exactly looking at the case where the quantum fluctuations can become large with respect to the classical, threatening to invalidate our perturbative description. So we need to turn to a different approach here to model these perturbations. And in fact, that approach was developed by Alexei Starodubtsev, Andrei Linde, and others in the 1980s, and goes by the name of stochastic inflation. So one way to keep track of this non-perturbative, non-linear evolution of the large-scale perturbations is to split the field into a small-scale UV part and a large-scale infrared part. So we're introducing a coarse graining scale. And there's a natural scale in the expanding universe, but it's the Hubble scale. So the infrared part is basically the super Hubble long wavelength part of the field. The UV is a small scale sub-Hubble fluctuations. And in this regime is where we can use the standard techniques to quantize the fluctuations of the field on small scale about a classical background. But then we extrapolate that forward with the expansion of the universe that constantly moves modes from the small scale UV regime into the infrared regime. So what were initially quantum fluctuations become stretched, go into a squeeze state on large scales, and we can treat them as an effectively classical contribution to the field on large scales, but where there's a constant stochastic noise term affecting the evolution of the infrared field from this as modes cross this coarse graining scale. Once they're in that large scale regime, then we can use the nonlinear evolution. And in fact, at leading order, that is just the evolution of the homogeneous and isotropic background cosmology. So this is what we sometimes call the separate universe approach to modeling the long wavelength evolution of the field here. It's the leading order behavior in an expansion in spatial gradients now on large scales. And that's been studied, so say for many years, since the 1980s. We can use either a Langevin equation to describe the stochastic evolution of the field. So here I've written the evolution of the field with respect to time, measured in terms of that expansion variable n. And in this stochastic approach, you've got a classical drift. Here I've used the standard slow roll approximation for this classical drift and introduced the stochastic noise term, which is now a quantum, you can think of as a quantum diffusion term. This is the evolution for the infrared field phi here. I should have identified with phi IR, the infrared field before. And now the small scale modes are contributing this stochastic noise term to the evolution of these fields. And this can be recast as, so this is, Langevin equation would describe the evolution of a particular realization, in a particular region of the universe as we follow that forward. Or we can try to model the evolution of the ensemble of the probability distribution for the value of the field with respect to time as this Fokker-Planck type equation here, where again we can identify a classical drift term for the evolution of the probability distribution plus this quantum diffusion term. So you can think of this as a differential operator acting on the probability distribution to give the time evolution of the distribution of well, this field or indeed many fields during inflation. And that's been studied in often thinking about what this might tell us about the distribution of field values, perhaps at the beginning of inflation or early on during inflation. But as Alexei pointed out, and indeed was in his early work in the 1980s, the realization that you can actually use this to study invert the problem here, and instead of thinking about how the field value evolves with the time n, the time, that's the number of e-foldings, the expansion of the universe n, you can invert the problem and ask the question as to how long inflation lasts, starting from some field value. So from this field value phi, if you invert the problem, you have a fixed field value, and you study the distribution in the number of e-folds, the time it takes to get to the end of inflation here. And as identified earlier, the primordial density perturbation, we can then reconstruct from the perturbation delta n with respect to the number of the perturbation in the expansion from this initial field value to the end of inflation compared in a local patch compared to the average value in the universe. So this becomes a first passage time problem where the duration of inflation from some field value to the end of inflation becomes a stochastic variable zeta. And well, first of all, we can reconstruct some of the results that we're used to calculating in a perturbative approach. So we can calculate, for example, the 2-point correlation function, or therefore the power spectrum of fluctuations in an inflation model. So here on the left, I've got the sketch of the power spectrum, log plot for the power spectrum as a function of the field value phi. In this model of inflation, which is just a monomial plus a constant term. So the evolution tends to be dominated by the classical evolution at large values, but then as the constant term comes to dominate, then the classical evolution actually comes to a stop in slow roll inflation. And in fact, you can see that corresponding to the divergence of the power spectrum when you calculate that perturbatively about the classical background, because the background solution has this singularity as the field value approaches the end of inflation, then the classical evolution becomes small and the quantum evolution is much larger. And classically, you would have, using that, perturbing about that classical result, you get an apparently divergent power spectrum as the field value tends to 0. But what you see happens in the full stochastic treatment is that the quantum fluctuations continue in some sense the evolution of the field. And if the end of inflation here is an absorbing boundary condition, then there's a finite duration of inflation to the end here. And the perturbations about that, therefore the power spectrum fluctuations about that background tends to, in this case, a constant value. So you actually regularize the divergence in the classical evolution from this stochastic picture, where we include into the background the quantum diffusion of the stochastic field. So, but crucially for this idea of calculating the abundance of primordial black holes, what we can do in the stochastic approach is calculate the full probability distribution function for the fluctuations zeta, or therefore the fluctuations in the number of e-folds n. And we sort of showed how to do this in a paper in 2017, where we constructed a characteristic function which includes all the moments of the distribution. It's the expectation of e to the I, and then we've got this dummy variable t times n, the number of e-folds. And that characteristic function obeys a differential equation. So if we can solve this differential equation for the characteristic function and invert it, we can get the full probability distribution. Now, this is a probability distribution now for the number of e-folds. The stochastic variable is the number of e-folds as a function of the initial field value phi. And so we were able to, again, in a simple model here, get analytic results for the full probability distribution function, which is approximately Gaussian, where in this case, where the quantum phase here is short, then you're dominated by this classical evolution, and the curves on the left-hand side here are basically Gaussian curves. But at large values of n, if you ask where are the fluctuations becoming largest, then eventually this peak turns over into an exponential tail. And it's no longer a Gaussian suppressed exponential tail, it's a simple exponent, the exponential tail here. And it's been argued more recently in this paper by Esquiaga et al. That in fact this is a generic prediction of slow roll models of inflation, that there will be this exponential tail at sufficiently large values of the number of e-folds n, and therefore at large excursions in zeta. So for large perturbations zeta, the large zeta limit is this given by this exponential tail. So this is very different. So this is why I'm saying that the usual Gaussian assumption for the probability distribution function breaks down in the far tail here. So this is the general argument given by Esquiaga et al. Is about is doing looking at this as a complex function, a function in the complex plane, and this exponential tail comes here from the poles in the complex plane, and the lowest pole gives the large late time limit, the large excursion limit of the probability distribution function here. So this is so I find this a very interesting system to study, looking at inflation in a different regime from what we often consider. So, but one of the challenges here is to really, so we're quite limited at the moment in terms of the analytic solutions that we have for the full probability distribution function. So getting into the analytic results out in the tail is challenging. It's tempting to look for numerical solutions, because it's very simple at some level to run many simulations of this these Langevin equations. We can reconstruct the probability distribution by just doing many runs of this stochastic equation. So the evolution of the field driven by this classical drift with a quantum diffusion term. And if we, and so naively think it's very straightforward to just do many runs and reconstruct the probability distribution numerically. So this is an example here where we've got simply a quadratic potential for the inflaton field, very familiar situation. To see some interesting results here, I've dialed up the mass here to be very large compared to anything that would much larger than would be acceptable as producing small density fluctuations in the CMB sky. But allow me to illustrate numerically some of the results that techniques that we're exploring currently in this paper, to appear soon, hopefully, with my student Joe Jackson. So if we do run this, we can indeed reproduce something which has a typical sort of normal kind of Gaussian distribution here for typical fluctuations for the typical results here. But if we drill down into, if we're interested in the tail of the distribution, if you imagine going down to look for probabilities down at something like 1 part in 10 to the 8, well, we'd have to get very far down into the tail here. And this is a run produced with something like 200,000 simulations. So if we change from the linear histogram here into, say, a logarithmic axis here on the y-axis for the probability distribution, we can see that these 200,000 simulations reproduce very well the peak of the Gaussian curve here. Typical fluctuations are indeed Gaussian. But as you get down into the tail of the distribution, these points begin to diverge away from the Gaussian. That's why we see this even for a simple potential where we have a large mass for the field here. Right? So I should say this is a result of picking a relatively large mass for the inflaton field. But you also see the effect that, of course, the error bars also becoming large as we get into the interesting non-Gaussian behavior here. And it certainly wouldn't claim that you can see this is necessarily becoming a simple linear exponent here in the tail. So the techniques were, and the problem is, of course, that most of your fluctuations are just, if you simply increase the number of simulations, you simply produce more simulations up at the peak of the distribution. And if we want to probe down into, say, 1 part in 10 to the 8, well, we need to do something like 100 billion runs just to produce one more point down at that level, at that low level of the probability distribution of 10 to the minus 8 or something like that.
Just to say 5 minutes, David.
But, okay, thank you, Bala. So the technique here, there are ways to deal with this numerically. We have to be more intelligent than just running more simulations. And so we can deliberately bias our simulations in order to explore the tail. And that's what I've shown here is that we can introduce a bias term here, an extra classical drift term with amplitude A here relative to the Hubble rate. And that basically, what I've got on the right here is a contour plot of where our simulations are actually ending up. So we're sort of biasing the simulations to produce large deviations from the mean of the distribution, which here is around about 10 e-folds to the end of inflation. So here we're biasing the simulation to get up into 13, 14 e-folds to the end of inflation. But then we can use these results as long as we reweight the likelihood of these points occurring in the original system. But because we've got a Gaussian noise term here in the system, we know the probability, we can basically work out this probability to reweight the distribution. And what I've shown on the left here then is the numerical results we can produce in a case like this, where different biases produce these different distribution of points, and we can basically dial up the bias to probe further and further into the tail of the distribution. And in fact, the error bars here I've magnified by 10, so you can see that the error bars for a particular distribution are narrowed at one point and then grow again eventually. But we can dial up, we can run different simulations to probe different parts of the distribution. So as you see, as we evolve from the purple to the pink to the gray here, the error bars evolve from the purple to the pink to the gray. And we've probed down not just to 1 part in 10 to the 8, but 1 part in 10 to the 20 or more here. So we can do things numerically. I need to wrap up, but I will set up the problem at least of what we need to do next is go beyond slow roll, because in fact, the sort of models people have proposed for studying for producing large density fluctuations typically is introducing a very flat part of the potential late on during the evolution of inflation. And that tends to disrupt, in fact, it needs to, in some sense, needs to disrupt the standard slow roll evolution. And so the sort of evolution one finds is what one can call ultra slow roll. So we need to study the stochastic equations in this different regime here of ultra slow roll. And that reveals the fact that in general, we have a 2-dimensional system for the field and its momentum pi. The quantum fluctuations, or the stochastic formalism in that case, was analyzed in this nice paper by Gran and Venin. In slow roll, we make certain approximations to reduce it to a one-dimensional system. In the ultra slow roll limit, in ultra slow roll, we need to make a different approximation. We can't reduce it. It cannot be reduced to a one-dimensional system. We actually have to deal with a two-dimensional system. Unfortunately, that gives us a partial differential equation to solve for the characteristic function, which makes life more difficult. If you want to find out more about how to study that, I'd direct you to our paper in 2001 here, where again, we were able to show some numerical results about how, again, the classical singularities in the classical evolution, in this case, studying the average expansion number of E-folds here, can be normalized, corrected by this, including the quantum diffusion. But nonetheless, we still expect to see non-Gaussian behavior in the tail of the distribution. So I'm going to wrap up. I hope I've given you a flavor of some of the calculations that we can do now to study large fluctuations in inflation. So this is very much motivated by the idea of studying primordial black holes that could be produced from inflation. But it would be interesting to understand if this has implications for other collapsed objects at early times in cosmology, or other applications for extreme fluctuations of the primordial density field. As I say, we can do that using the stochastic approach. We can construct the full probability distribution for the number of E-folds from a given field value, and therefore reconstruct the probability distribution for zeta. And the challenge now is to do that for some of the particular models, and they're often quite fine-tuned and delicate models of inflation that produce large, offer the possibility of producing large fluctuations in the density field. But I think to really study those large, rare density fluctuations, the correct way, the fully correct way to study that would be to use the stochastic approach, because it can really go beyond the usual perturbative results. But I should stop there, and happy to answer questions. Thank you.
So thank you very much, David, and I hope you are all listening me. So I see Philip Mannheim with his raise his hand. So there is a question, please.
Yes. Well, first of all, David, thank you for that talk. I'm an outsider, so I found it very interesting. Let me ask you one very quick question. When these density fluctuations collapse into black holes, what do the black holes contain?
So they're forming from the radiation plasma. So you really, you're in the almost a standard hot Big Bang cosmology with plasma at whatever the appropriate temp, so if it's 10 to the minus 6 seconds, you've got maybe protons and neutrons already by that point, but mainly electrons and photons, of course. And yes, therefore you need a very large density perturbation for that to collapse directly. But if you get these very large density fluctuations in the plasma, you collapse, and so it is just elementary particles of the plasma really that are collapsing inside the horizon to form the black holes.
I suspected that they would be primarily baryonic, but then you would have a problem if they're going to be dark matter today, because that would mean that the baryon density in the universe would have to be not just the BBN value, but the dark matter value.
Yeah. So no, these are.
So that it seems like a problem.
Yeah. So no, these are not. So well, the simulations I believe that are done are really. I mean, so people are modeling a radiation fluid, typically here, I think. So they are. So they're assuming you've got the coupled plasma. So yes, it includes electrons, baryons, photons, but Yeah, it's an interesting question. I mean, if it's at very early times, even the dark matter would be coupled, but these would be that would correspond to small primordial black holes forming. These stellar mass primordial black holes would form after the dark matter has decoupled. But I guess it's the dominant gravitating matter at the time is really the radiation coupled, scattering off the photons, and baryons. But so it's the relativistic photons as primarily indeed collapsing into black holes.
Oh, so
you don't need any. Yeah,
I thought there were sort of theorems that massless particles can't collapse into stable, static, spherically symmetric sources.
Well, they are coupled, so it will be important that they're coupled. They're not free streaming out. They're not allowed to free stream out because I guess they're tightly coupled. So the electrons, for example, will be subdominant in the total mass, but nonetheless they play a role in constraining the photons. I should say I'm not an expert, and if any experts are out there.
Yes.
But as I say, the modeling, that said, the actual numerical models, I think, are fluid models. So, yeah.
Okay.
But I think the idea would be that the photons are constrained by the collapse, their own gravity, and then they're not free streaming because they're tightly coupled to the plasma.
Mm-hmm. Okay.
Well, thank you. And now we have a question from Jinsu Kim, if I'm properly spelling it. Good afternoon.
Right. Yeah. Thank you. Thank you for the nice talk. Maybe I have missed it, but in the single field inflation models, some sort of fine tuning is needed to produce primordial black holes.
Yes.
I was wondering if that can be relaxed if you consider the non-Gaussianity.
Yeah. Well, yes. So maybe. So this is a work in progress, I think, really, to answering that question, because certainly for many years the calculations all assumed a Gaussian distribution. So to some extent, there's relatively little studies of the effect of this non-Gaussian tail. There are just some early studies. Maybe on my next page I have some of the challenges. So there's recent papers, for example, by Biaghetti and Kitajima et al., who study fluctuations in a non-Gaussian distribution with a particular exponential tail, which is motivated by, well, it's ultra slow roll, but it's a classic. It's a sort of classical limit of ultra slow roll, but nonetheless it shows this an exponential tail, and they've looked at the effect of those. I think we're a little bit away from actually then going back from that to really understanding what the effect would be if we're thinking about fine tuning of the inflaton potential, for example, what that means. It might ease the fine tuning. You're absolutely right that to get what the correct abundance of black holes of any particular mass requires even in the standard calculation, assuming a Gaussian, you need that. You're probing down into this tail, exponentially suppressed tail. You're very sensitive to producing, to any change in that Gaussian distribution. Here it might be less sensitive because it's not so, the tail is not so suppressed in the sense with a simple exponent, but nonetheless there's a lot of coincidence apparently to required. I imagine you still have an exponential tail. It still looks quite likely that you will have some kind of fine tuning there.
I see.
But yeah, I haven't done the full calculation yet, so I'll let you know in a year's time. Or I say there are some initial calculations here.
I see. Interesting. Thank you very much.
Thank you very much for the question and also for the answer. So as far as I see from my time counting, we still have 2 or 3 3 or 2 minutes. If anyone has a quick question for a very brief reply answer. Oh yes, there is there from Sikander. So let me just put Sikander, if I may. So Sikander, go ahead.
Hi, thank you. And thank you for the nice talk. It's just a quick comment that your second order differential operator, LFP, looks a lot like a hypergeometric differential operator. And of course, their equations are, their solutions are known as hypergeometric functions. So
yes, there are.
This one, exactly.
Yeah, that's right. So that's right. So actually, the problem we've been studying, I mean, certainly people have studied this Fokker-Planck equation in particular cases, and in fact, Alexei Starodubtsev would know better than me the solutions in that case. We have in our case, we have, I think I just wrote it down here in schematic form. Where are we? Here. For our characteristic function, we actually have the adjoint of that operator, but it's
right,
of course very similar. And indeed, there are some cases, depending on basically what the coefficients are in that operator, where you can get hypergeometric solutions. Yes. So in this paper in 2017, we had particular, but it's in particular cases you can find solutions here. These coefficients, as you can see, kind of come from H, and H is typically modeled by via phi. So for polynomials, I think, for example, you can get solutions here. Sorry, monomials, potentials, you can get solutions. Yeah.
Cool. Thanks. I just wanted to point that out. Thank you.
Is there another hand? Do we have time, Paolo? Are you there, Paolo?
Okay. I think Paolo lost his connection, but coincidentally, it's my. I want to ask a question, so maybe I can continue. So, thanks for the nice talk. I have a question. So you have described about scalar fluctuations. So what about tensor fluctuations? Do they play any role in primordial black hole? Or
as far as I know, probably not in primordial black hole formation, but welcome to be told otherwise. So typically there's a interesting recent paper by Gemmassimo Tassanato looking at applying the stochastic approach to tensor fluctuations.
Mm-hmm. Yeah.
But typically they don't contribute. So once the tensor modes, as Alexei Starodubtsev was saying in his talk, of course, they are also stretched by the expansion of the universe. They can be quantized on small scale. So you have an inhomogeneous universe on very large, if you look at it on very large scales above the Hubble scale, when you consider all these fluctuations building up from the small scale fluctuations and producing tensorial perturbations. But locally, in the long wavelength limit, their effect on the expansion becomes small for very long wavelength gravitational waves. So in the long wavelength limit, typically they don't contribute to the background expansion. They don't affect in particular, for example, here I'm interested in the time from a particular field value to the end of inflation. They're not included in this analysis, but I think that's correct because they don't contribute to the expansion rate in this infrared limit.
Okay, I understand. Thank you.
Well, thank you. I'm back. It was just a minor internet problem, so I guess we can proceed. And thank you very much indeed to an extremely interesting talk by David once. And now it's up to Latham Boyle. I apologize if I'm not properly spelling it correctly, so my apologies.
The second pronunciation was perfect.
Boyle, sorry about that. I apologize.
No problem.
So, and The talk will be about a two-sheeted CPT symmetric universe. So up to you, please.
Okay, thank you very much. So first of all, I have to say I'm traveling at the moment, and in the hotel where I am, the people at the desk told me this would be a quiet spot to give the talk. I think it's less quiet than they anticipated, so I apologize if there's background noise. Hopefully you can hear me. Yeah, so I wanted to try to tell you about this alternative model of the early universe, well, and of the late universe, really, that I've been working on with in the past several years in close collaboration with Neil Turek, and in particular, this will be about these 5 papers, these first 2 which appeared a few years ago, which were also with my former master's student, Kieran Finn here, and then these 3 more recent preprints with Neil Turek from the past several months. In short, we think that it's a model in which there are a few simple principles that end up having a surprisingly large amount of explanatory power about the some of the observed features of the universe, and also predictive power for future experiments. So I'll try to sketch why we're excited about it. The first 2 papers here are sort of introducing the idea, the idea of the CPT symmetric or two-sheeted universe, and why it gives a very elegant explanation for the dark matter. And so that'll sort of be part 1 of the talk. The 3rd and 5th papers here have to do with what effect it has when you take account of the fact that the universe has a positive cosmological constant, and presumably therefore has a future de Sitter boundary awaiting us in the future. And then the 3rd part of the talk will be about this 4th paper, which has to do with a novel mechanism for a very non-trivial cancellation of the vacuum energy and the 2 terms in the Weyl anomaly in the standard model, and what that has to do with the whole story. So let me dive in. So part 1, introducing the CPT symmetric universe idea and what it has to say about dark matter. Okay, so let me start with this cartoon picture of the expanding universe. So here I have conformal time tau running up the page, and I have the universe represented as a kind of inverted lampshade, showing that it's been expanding. And the idea is that this is us living up here long after the Big Bang, and we look back with our telescopes, and we can't see all the way back to the Big Bang, but we see awfully close, a few 100,000 years, or more indirectly, back to a fraction of a second after the Big Bang. And what the observations tell us, very strikingly, is that the closer we look to the Big Bang, really the simpler it becomes, and it turns out to be incredibly simple. So to a very good approximation, this surface, a fraction of a second after the Big Bang, appears to have been a maximally symmetric 3 geometry, indeed a flat 3 geometry. And then the perturbations away from that are tiny, and moreover, they're also as simple as can be. They seem to be perfectly Gaussian as far as we can tell, described by a perfectly power law power spectrum, perfectly adiabatic. The power spectrum seems to be almost exactly scale invariant within a few %. So it's all clearly some very important clue about how the universe began, or what went on in the early universe. And the question is, what is that clue trying to tell us? So the traditional, or let's say the most popular interpretation, is that, okay, as we look back toward the Big Bang, things seem to be getting simpler and simpler, but that actually, if we went back further, there was an earlier messy epoch, and then there was a period of inflation which accelerated the scale factor and cleaned up the mess, basically. And so that's one possibility, but I want to try to investigate this other possibility. I want to try to investigate this other possibility to try to sort of take the observations more at face value. The universe seems to get all the way back to a fraction of a second, as far back as we can see. I mean, it's important to keep in mind that there's no observational or theoretical evidence for this earlier messy stage, and so it might just be a figment of our imagination, and all processes having to do with cleaning up that mess might be sort of solving fictitious problems. So the question is, what if we try to take the observations more at face value? As we look back to a fraction of a second after the Big Bang, it seems that the closer we go to the bang, the simpler things get. Taking the observations at face value, what I mean by that is assuming, well, maybe for some reason that is the way things are. Maybe somehow, maybe for some reason, as the closer you get to the Big Bang, things just get simpler for some reason. So let's imagine that's how it is and see where that line of thought leads us. Well, as a first step, before proceeding, let's do Penrose's trick and rescale the space-time conformally to make the sort of causal structure of the Big Bang in our past more explicit. It's really a spatial hypersurface. So I've just stretched out my lampshade into a straight cylinder. Fine. So if we want to take the simplicity of the early universe seriously, well, then we know what the metric was like at early times. It was really just the flat metric times a conformal factor, and if we follow it back far enough, it hits a singularity, but it's the simplest sort of singularity you could imagine, much simpler than a generic GR singularity. It's just a momentary zero in the scale factor, in the conformal factor, a squared of tau, and moreover, that zero is as simple as you could imagine, because in the early radiation-dominated era, the scale factor is just proportional to tau, linearly proportional to tau, so it's just a simple analytic zero. So unlike with most singularities in GR, there's no ambiguity about how to analytically extend this one. And so let's try to do that. Well, if we do that, so now tau, instead of cutting off tau at tau equals 0, we let it extend to negative and positive values. Then the first thing we notice is that we get this now extended cylinder that has a new symmetry that we didn't notice, a new isometry that wasn't clear when we were only looking at the upper part of the cylinder. Namely, an isometry under tau goes to minus tau, basically flipping over the whole hourglass. That's interesting because a consequence of that new isometry is that there's a preferred vacuum state for quantum fields living on this space-time, the CPT symmetric vacuum state. So we're familiar with the fact that in Minkowski space, there's enough symmetry that there's a preferred vacuum that respects all of that symmetry, and all inertial observers agree on that vacuum. But of course, in a general curved space-time, there's not a preferred vacuum state. Different observers at different parts of the space-time, different inertial observers, will disagree about what the zero particle state is. And in particular, in FRW space-time, that's usually the case. The FRW symmetries are not enough to determine a preferred vacuum, but FRW symmetries plus CPT is enough. Okay, and so we want to sort of take this, take the symmetry of this analytic extension to be not an artifact. We want to suppose maybe it's a hint, and try to follow that hint. So we want to take this supposition that maybe the universe actually does not spontaneously violate CPT symmetry, as you might have thought if you only looked at the upper half of the spacetime, and see where that leads us. Okay, so the first thing to say about where it leads us is, well, let's consider a matter field living on the spacetime. In particular, I'm considering a spinor field here. And so the usual way we quantize it is we decompose it in a set of solutions of the Dirac equation. There are the positive frequency solutions psi and the corresponding negative frequency solutions psi c, the charge conjugate solutions. And we quantize it by promoting the coefficients in front of the positive frequency solutions to the annihilation operators of the particles, and the coefficients in front of the negative frequency solutions to the creation operators for the corresponding antiparticles. But again, the key point is that we needed to split up this basis of solutions into positive and negative frequency solutions. And in Minkowski space, all inertial observers would agree about that, but in curved space-time in general, they don't. And so an observer long after the Big Bang would split up the solutions in one way. An observer long before the Big Bang would split up the solutions in a different way. And consequently, they would define two different vacuum states, which I call 0 plus and 0 minus, but neither of those is CPT symmetric. Neither of those respects the full symmetry of the spacetime. They're two inequivalent vacua, and they're exchanged by the symmetry. On the other hand, we can define a new vacuum that is CPT symmetric if we choose the mode functions to have this extra property that basically the solution at time tau after the bang is equal to the charge conjugate solution at a time minus tau before the bang. Then that does define a vacuum state that is CPT symmetric. Okay, so that's, and the importance of that is that then if we take the CPT symmetric mode functions and just re-express them in terms of the basis of solutions that a late-time observer like us would use, that the corresponding coefficients, the Bogle-Uboff coefficients in the expansion, alpha and beta, can be calculated analytically. And then we can calculate according to a late-time observer like us, using our number operator, this A plus dagger, A plus, what is the expectation value of the number of particles if the universe is really in the CPT symmetric state, 0 sub 0. Okay, and so famously that is just given by the square of this Bogle-Uboff coefficient beta. And the details are not important here, but so that in turn is given by some formula which depends on the ratio of the Planck mass to the mass of the particle in question, the mass of the spinor field. And so in other words, there's a phenomenon very much like Hawking radiation, or I should also say that so usually called Hawking radiation, probably Starobinsky's name should be in there, since of course he also played a very pioneering role in discovering it. That it's like Hawking radiation in the sense that in Hawking radiation you have the black hole is in one state, but an observer far from the black hole defines a different vacuum state, and so according to that distant observer, the black hole is interpreted as emitting particles. Similarly here, we're assuming the universe is in one state, the CPT symmetric state, but according to the late-time observer, far from the bang, the universe, they define a different vacuum state. We, I should say, define a different vacuum state. And so according to us, there is a flux of particles that seem to be emerging from the early universe. Fine, so what does it have to do with dark matter? Well, let's try to now apply these ideas to the standard model. So here is a list of the particles in the standard model. These are the bosons here, the gauge fields and the scalar field. And then there's the fermions. There's the quarks in one generation, or the left-handed down quark, the left-handed up quark, right-handed down, right-handed up. Those come in 3 colors, and then there's the corresponding leptons, the left-handed electron, left-handed neutrino, right-handed electron. And if we were in the minimal standard model with massless neutrinos, that would be the whole story. Ever since the discovery of neutrino oscillations and neutrino masses, it's the simplest renormalizable explanation for that has been to add right-handed neutrino to the story, which also completes the sort of pattern of particles in the standard model in various ways. Now, if we don't include the right-handed neutrino, there's just no remaining dark matter particle in the standard model. I mean, in the minimal standard model with no right-handed neutrino, there simply is no remaining particle that we haven't observed that is stable that could be the dark matter. Once we do include the right-handed neutrino, well, there's 3 of them because there's 3 generations of these fermions. And 2 of them we know are unstable and decayed in the early universe, but 1 of them might well still be stable, and that is really the last possible dark matter candidate in the standard model. So let's try to assume that that is the dark matter candidate and ask what would the prediction be about that particle if this CPT symmetric idea was right. So in other words, we're going to ask that the one remaining dark matter candidate in the standard model is stable. That corresponds to assuming that the standard model has an extra symmetry that stabilizes that particle, simple symmetry you can impose on the standard model Lagrangian. And once you do that, it's easy to take the formulae that I showed on the previous page and calculate the abundance of that particle that emerges from the early universe. So in particular, you can calculate this dimensionless ratio, the ratio of the number density of those particles, those neutrinos, which will be our dark matter, to the radiation density. And it's given by basically the ratio of the dark matter mass divided by the Planck mass to the 3/2 power. And so you can work out that if the dark matter mass, if that right-handed neutrino mass is this value, 4.8 times 10 to the 8 GeV, then you get the right abundance to match the observed dark matter density in the universe today. Or phrased another way, in our picture, if this one remaining dark matter candidate is stable, that turns out that same symmetry that makes it stable also makes it completely dark. It doesn't talk to the rest of the standard model. It's purely a free particle on a gravitational background. So it's inevitable by the previous calculation that if it's in the CPT symmetric universe, that it's produced with a certain abundance. And once we measure that abundance, we get a measurement of its mass, which is this value. Okay, so that's where the dark matter comes from. Now let's talk about what some of the observational consequences of that idea are. So it's because this particle is completely decoupled, very dark, it's very hard to observe it directly. In principle, it doesn't have to be 100% stable. The symmetry could only be approximate, and then you could hope to see it slowly decaying at a certain, with a decay width at a certain very well-defined frequency given by its mass. But I mean, with decaying into particles with very well-defined energies, I should say, at half of its mass. But we think that's probably just wishful thinking. So probably it's stable. In which case you unfortunately can't observe it directly using direct detection experiments. What you can do is observe the consequences for the light neutrino sector that you can observe. So I remind you that in the standard model with right-hand neutrinos, there's 6 mass eigenstates. There are these 3 heavier ones, 2 of which are unstable and decay in the early universe, which is good. Those can do leptogenesis and explain the matter-antimatter asymmetry. One of them, in our scenario, is the remaining stable one. That's the dark matter. And then there are the 3 light neutrinos that we can observe. And I remind you that with oscillation experiments, we've detected the differences between those mass eigenstates, but we haven't measured the overall offset from 0. So we don't know what the overall mass scale is. And again, there's 2 possibilities. One is called the normal hierarchy, where the pattern of neutrino masses kind of looks like this: 2 that are lighter and 1 that's heavier. And then the inverted hierarchy, which looks like this, where 2 of the eigenstates are heavier and 1 of them is lighter. In our approach, in the standard model, I should say, once this remaining right-handed neutrino is your dark matter candidate, you're stuck with the fact that the lightest of the 3 light neutrinos is massless. So it fixes this size scale. We say that actually this offset from 0 is 0. Okay, there is no offset. And so that means that the sum of the 3 light neutrino masses is predicted to be the minimum possible value, which is 0.06 eV in the normal hierarchy, or 0.12 eV in the inverted hierarchy. And that is something that cosmological experiments are really closing in on testing. I'm told that about 5 years from now, that number is expected to be measured by one experiment or another, maybe Euclid first, maybe no. Anyway, there's several competing experiments that each of which might get it first, but they're expecting to get that number measured to something like 20%. Within the next 5 years, and so yeah, our claim is that it should either agree with this value or this value within that error bar, and that if it doesn't, then this theory is not right. There's other ways to test it with laboratory experiments, which probably won't happen quite as fast, but in the future they will be tested in other ways. So we're predicting that the neutrino-less double beta decay rate has some definite value, which just depends, which is basically corresponds to the left-hand prediction on this figure. And it's the upper value or the lower value depending on whether it's the inverted hierarchy or the normal hierarchy. Another of our predictions is that this dark matter particle is very cold. It's very cold dark matter. So if evidence starts to favor warm dark matter or fuzzy dark matter, which are both very fuzzy, like scalar dark matter with very light scalar fields that behave like Bose-Einstein condensates, if experiments really start to favor those, either of those 2 types of dark matter, again, ours is ruled out. And finally, in contrast to inflation, the CPT symmetric vacuum predicts 0 primordial gravitational waves. Okay, so with that said, let me move on to part 2, where I want to talk about how so far I've talked about sort of some consequences of thinking about what happens when you analytically extend the universe backwards and take seriously the fact that you can analytically extend it past tau equals 0. Now I want to think about the fact that the asymptotic future is likely to be dominated by a positive cosmological constant and see what the implications are of that. Okay, so for starters, for simplicity, it's helpful to start with a slightly simplified Friedmann equation, where you notice here that I've included a radiation term, which is the thing that we expect to dominate at early times close to the Big Bang, a lambda term, positive cosmological constant, which is the term we expect to dominate in the far future, and then the spatial curvature, which could be flat or open or closed. But at the moment in this equation, I've not included the non-relativistic matter, the dust that you and I are made of, and then I'm going to put that back in the story later. But for starters, it's good to consider this. This is sort of the simplest FRW universe. It's the most complex one that we can solve, where we can solve the Friedmann equation analytically, and it's the simplest realistic model that gets the right asymptotics corresponding to our own universe. Radiation dominated near the Big Bang, lambda dominated in the far future. Okay, so the solution of this equation is this beautiful analytic function. It's this Jacobi elliptic function Sn. Here, the constants alpha, beta, and m, the details aren't crucial at the moment. They depend, of course, on the various parameters in this equation. So first, I've drawn the solution along the real eta axis. Oh, I'm sorry. I think I changed notation. Earlier in the talk, the conformal time was tau, and I think I mistakenly switched in these slides to eta. My apologies. Okay, so here I'm plotting the solution along the real eta axis, the real conformal time axis. And this is the part of the solution that we normally pay attention to. The universe starts at 0 scale factor and then expands to infinite scale factor when we hit the de Sitter boundary. And notice that in a universe with positive cosmological constant and radiation, there's just a finite range of conformal time between the Big Bang and the future boundary. And then this is the part of the universe that we were previously discussing, where we analytically extend back through the bang and consider the earlier branch with negative scale factor. And then the solution just repeats itself periodically. Okay, so here I've drawn a space-time picture of a solution like that. It's a kind of two-sheeted cylinder, if I draw it as a conformal diagram, where here we start at the bang, and then along the outside sheet, the scale factor increases through positive values from 0 up to infinity. And then we come around the pole, and then we come around the pole here, and it extends from minus infinity back to 0, and then 0 up to infinity, etc. So the periodicity in this direction is the wrapping around of the cylinder here. And then this circle in this direction is supposed to represent the spatial three-sphere if the universe is closed. So it's this kind of two-sheeted cylinder. Okay, very good. Well, so what I'm trying to argue for is I'm trying to explain to you some of the evidence. Why should we really take this sort of analytically extended picture seriously? Why should we think of it as having some reality and not just being a mathematical artifact? So I gave some evidence in the earlier, in the first part of the talk, that it seems to give a very elegant explanation for what the dark matter is. It turns the last remaining standard model dark matter candidate into a good dark matter candidate. So another bit of evidence is to look at the solution now in the complex eta plane here. So now this is the imaginary eta and the real part of eta along the two axes, and I'm plotting the scale factor. The blue circles are where the analytic function has a 0, and the white circles are where it has a pole, and then I've marked the poles of positive and negative residue with pluses and minuses. So these Jacobi elliptic functions have this property that they're doubly periodic in the complex plane. So they have two different periods, and so they form a kind of tiling of the complex plane. And so far we had been discussing the periodicity in the real direction, but let's think for a moment about the periodicity in the imaginary direction. In particular, one way to look at it is to say, we've been working with the conformal time eta, but let's try to compute the physical time t. Well, as always, the physical time is some integral of a d eta from 0 to eta. But now, you know, it depends how the contour wraps around these poles. It'll pick up different integer multiples of the residue at the pole, depending on how we wrap around the pole when we go from 0 to eta. You know, so if we want to go from here to here, for example, it depends whether we go this way, or wrap twice around here. Okay, so all of that choice of contour just introduces a uncertainty delta t in the physical time, which it turns out is exactly 2 pi I over the de Sitter expansion Hubble rate, the de Sitter 1 over the de Sitter radius, basically, which is exactly the usual expression for the temperature of de Sitter space. So there's a familiar fact that systems that are periodic in imaginary time have an interpretation as systems that are at thermal equilibrium at some temperature, and from the period in the imaginary direction of time, you can read off the temperature. So in this way, you read off that the temperature of this space is the usual de Sitter temperature, but now applied to this much broader class of solutions that include radiation and spatial curvature in FRW universes. Okay, so another bit of evidence is the following: that you get a kind of elegant new explanation for where the observed thermodynamic arrow of time comes from. By that I mean there's an observed fact, which is that the entropy of our universe seems to be getting bigger as we get further away from the Big Bang. And the question is, why is that? So to answer that, let's now add matter back into the story. So here's the simplest example of a matter field, a scalar field with some mass living on this background. And now, again, the idea is that the background that the scalar field is now living on has this. We've analytically extended it and seen that it has these extra symmetries that weren't apparent before we extended it. And our hypothesis is that those symmetries are not just mathematical artifacts, that they're real hints to be taken seriously. And so we want to demand that the solutions for the matter fields respect those symmetries, that they don't destroy them. So if we assume that the solutions respect the background symmetry, we also notice that the solutions are also analytic at the Big Bang, and that implies that there's kind of two ways to get from here to here, to get from a point on the outside to the inside sheet of the cylinder. We can either just use the assumed symmetry to jump the field from the outside to the inside, but alternatively, we can use analyticity to extend the value of the field around the bang and up to the inner sheet of the cylinder. And the fact that those two approaches have to agree with one another imposes a reflecting boundary condition on the field at the Big Bang. So we find that symmetry plus analyticity imposes a mirror-like boundary condition at the Big Bang. The Big Bang becomes a sort of mirror with which is exotic in the sense that it has its normal vector in the time-like direction. On the other hand, the solutions have essential singularities up at future infinity, so we can't analytically extend over the top, and so there's no analogous boundary condition at future infinity. So they're not analytic at the de Sitter boundary. And so we want to say that this gives a very simple new explanation for the observed arrow of time. The observed arrow of time arises because there was a very constraining boundary condition that forced the fields into a very special configuration at early times, but no corresponding boundary condition on the fields at late times. And so they started in a very odd place in phase space and have just been wiggling their way into more probable configurations ever since. Now, I explained that the field phi has certain reflecting boundary conditions, depending on what frame you look at it in. Actually, the tetrad, this field that squares to the metric that fermions feel, also has by a similar argument as reflecting boundary conditions at the Big Bang. They're the opposite sort of reflecting boundary conditions. And that turns out to have several correct implications for the primordial, for the observed primordial cosmological perturbations. It implies that there are no primordial vector perturbations, which agrees with what we see. It implies that there are no decaying mode tensor perturbations. Well, we already said that there were no tensor perturbations periodly, so that one is not so important. It implies that there are no decaying mode scalar perturbations, no decaying mode density perturbations. That's important. That agrees with what we observe. That explains why the scalar perturbations. Okay, thank you. That explains why the scalar perturbations are synchronized, so that all modes of a given wavelength are oscillating in sync, which is why you see the observed oscillation pattern in the cosmic microwave background spectrum, and lets you predict at what L values you'll see peaks and troughs. Okay, now finally, because we have this solution which is periodic in the imaginary direction in time, it is crying out for a thermodynamic interpretation, and in particular, you can compute the entropy of the space-time by computing e to the is around a period in the imaginary direction. So here I've taken this one fundamental cell in this periodic tiling, and I've identified the left and right at the top and bottom. So it turns into this torus. And then I want to take the integral of I times the action around the red loop, and it turns out it's a topological invariant. I can deform that loop any way I want, and I get the same value. And in that way, I get a calculation of the entropy of these space-times. And the key point, which is explained in a recent paper from last month, is that the entropy is largest. The entropy is largest for spacetimes that are flat. So flatness is favored entropically by this gravitational entropy calculation over spacetimes that are either closed or open. And moreover, when you include perturbations, either scalar or tensor perturbations, you find that they cost entropy. So again, they are thermodynamically disfavored. So we want to say this gives a quite fundamental possible new explanation for the observed homogeneity and isotropy and flatness of the universe. Finally, in my last few minutes, I just want to give a glimpse of a third result, which is related to the previous two parts, which is about a new way to cancel the Weyl anomaly, both terms in the Weyl anomaly and the vacuum energy in the standard model, and how it, in the context of this cosmological model, also gives a new explanation for where the primordial perturbations, scalar perturbations, come from. Okay, so I remind you that there can be both global and gauge symmetries, and they can both have anomalies, but normally we think it's okay for global symmetries to have anomalies. That's consistent, but gauge symmetries, we think their anomalies should cancel in order for the theory to be consistent. And here I've taken a picture from Peskin and Schroeder where he shows all the different triangle diagrams that have to cancel in order for the gauge and gravitational anomalies in the standard model to cancel, and they do cancel each separately, so it's very impressive cancellation. What about local scale invariance? That's another possible gauge symmetry. Weyl and Dirac and Dickey and others had argued that that was a very natural extension of Einstein's general covariance. General covariance is about the fact that physics shouldn't depend on how you describe it in terms of choice of coordinates, local choice of coordinates. Weyl and Dickey and Dirac and others were saying, well, another freedom should be the freedom to describe the physics in different units and have that be a local choice also. Well, now in the standard model, what's the status of that? Well, if we ignore the Higgs field, if we ignore all the terms of the Higgs fields, the remaining terms in the standard model are Weyl invariant, classically. But even then, the symmetry is anomalous. There's a famous formula for the Weyl anomaly. This trace T term should vanish if the symmetry is not anomalous, but instead, these coefficients A and C are given by this famous formula in terms of the number of scalar and spinor and gauge fields in the theory. And since they all come with positive coefficients in both of these equations, there's no cancellation. These A and C coefficients are positive, and the anomaly is there. So in short, it turns out there's a new way to cancel that anomaly, which is, well, there's two ways to conformally couple a scalar field in 4 dimensions. There's the standard way, and there's a second way in which the scalar fields are dimensionless. And when you include such dimensionless scalar fields, they add an extra term to the anomalies and to the vacuum energy, which was originally calculated by Ripken and Zeitlin in '84. And you notice that it comes with a minus sign here. And so now it suddenly becomes possible, actually, there is a unique solution which causes both terms in the anomaly and the vacuum energy to cancel. And that is when the number of fermion fields is exactly 4 times the number of gauge fields, and the number of ordinary dimension 1 scalars is 0. So this first prediction is very striking because it matches the standard model. In the standard model, the number of gauge fields is 1/4 of the number of fermion fields if you include all 3 generations. You have to include all 3 generations in the right-handed neutrino in order for that to be true. So that's very striking. And then, meanwhile, on the other hand, it seems to require, this n0 equals 0 seems to require that the Higgs field, the observed fundamental scalar in the standard model, is not fundamental. It must be composite or emergent or something like that. Now, we're excited about these new dimension 0 scalar fields because they automatically have a scale invariant spectrum, even in flat space. So we think they're made to order to produce the primordial perturbations. And Neil and I are in the middle of writing a paper about this right now. So if you have time, let me I apologize for zooming through those last few slides, but no pun intended. But let me just jump to my summary slide. And thank you for listening.
Thank you very much. It was really interesting, and I appreciate the summary. It's quite clear. So I now ask if there are any questions. Philip Mannheim has just put his hand up, so please.
Yes. Well, first of all, Latham, hello.
Hello, Philip.
Finally, good to meet up with you, even if it's still virtual.
Yes.
I have a comment and then I have a question. The comment is, what you're doing, at least the last part of your talk, is very similar to stuff that I've been doing, where I've looked at psi bar psi dropping its dimension from 3 to 2. And you're basically taking the scalar psi bar psi and dropping its dimension from 1 to 0. And that's really the heart of all of these studies is this drop in dimension, and that's what you're doing.
Psi bar psi is a Dirac fermion?
Dirac fermion, yes. Yes, the canonical dimension of psi bar psi is 3, but in my work I've found reasons for why it drops to 2.
Okay, I'd appreciate it if you could send me that. Yeah.
That's fine, I will do so. Second comment is, and I'll talk about this myself in my talk, is there is another way to cancel the Weyl anomaly, and that's to have gravity itself do it. And that actually works in conformal gravity. Now, I have a question for you, and that is that you've obtained a very nice relationship between the numbers of fermions and bosons and so on, which looks very close to the standard model. But unlike the triangle anomaly, the trace anomaly is renormalized in higher orders of perturbation theory. And so I don't know that you can maintain those relations unless you have some no renormalization theorem.
Well, we don't do it that way. As far as we know, there's no non-renormalization theorem, but we discussed this in our forthcoming paper that, so yeah, at one loop, I don't know about higher loops, but at one loop, there's one contribution to the Weyl anomaly, which just comes from the free field content of the theory, and which is non-zero on a curved background. And that's the part that I discussed canceling in the talk. And then I think what you're alluding to is that then there is also at one loop, there's a contribution coming to the Weyl anomaly from interactions between fields, which is already present in flat space and indeed is non-zero also in the standard model. Another contribution from trace T that would already be there in the standard model on flat space due to the fact that the couplings run. And that can be canceled by having these new scalar fields couple, a linear coupling between these new scalar fields and the anomaly term in the action, the normal scale anomaly term in the action, like the f squared beta times f squared term in the action. That describes those anomalies. So that can be canceled. So all of the one loop anomalies, including those ones coming from interactions, even though I didn't mention them in the talk, can all be canceled. About two loops, I don't know. I don't even know if the sort of anomaly up to two loops is known, or if it is. We haven't thought that far. I mean, we're just very struck at the moment by this fact that everything works out so nicely at one loop. And we think it's very likely to be a hint, but I don't think we definitely don't claim to to know that it cancels to all orders.
I wasn't trying to pour cold water on what you're doing.
No. So yeah, no. But anyway, it's certainly a very good point to raise, which is that we don't claim that like you say, unlike the other anomalies where once you know they vanish to one loop, you know it to all orders. That's not true for the Weyl anomaly. So that's a very good point.
Okay.
Thank you. And there is Robert Brandenberger. He raised the question, what can you say about the spectrum of scalar perturbations? And then said that you answered the question, but then again, he put a comment on, can you explain again why there are no gravitational waves? I don't know if you want to reply or comment or add to the conversation.
In brief, the reason there's no primordial gravitational waves is because the same calculation that I did for the fermions essentially applies up to minor details also for the gravitational waves. If you treat them as just as a spin 2 field living on the background, that in the limit that the mass goes to 0, that calculation predicts there's no discrepancy between the CPT symmetric vacuum and the late time vacuum. So you predict 0 particles according to the late time observer if the universe is really in the CPT symmetric vacuum, including the gravitational waves.
Thank you. We might have time for one quick question and summarize reply. Please.
Oh, okay. I will ask a quick question then. Hello. Thank you for the talk.
Hello.
I have a question about the action upon the scalar that you need to cancel the anomaly. So you have like a 4 derivative scalar field. Would you see any Stochastic instability?
So that's another very good question. We discussed this in our paper. This is a very interesting theory. There have been a number of papers over the past several years. One by two very good ones by Philip Mannheim and Carl Bender. There's another one from a few years ago by Salvio and Strumia. There's I'm not going to forget all the. I'm going to forget the names of the. I'm not going to do a good job. Sorry, I can't list everybody. There's been a kind of little industry working on this sort of theory. And so the first thing to say is that different papers say it in different ways, but it's a bit like the Dirac-Lagrangian. That if you try to naively quantize the Dirac-Lagrangian, it looks like it has negative energies. It doesn't give a sensible theory. But then there's a way to. There's certain sign choices of signs here and there that fix it up. You use anti-commutation relations and anti-commuting fields, etc. And in short, people have found ways to. There's an analogous story with these with this particular type of Lagrangian, which is an example of something called the Pais-Uhlenbeck oscillator. That if you try to quantize it in the traditional way, it has ghosts. Doesn't give a sensible theory. But there's an alternative way to quantize it, which is described by Bender and Mannheim as PT symmetric quantization. But it's described essentially the same thing as described by Salvio and Strumia as poly-Dirac quantization. They had pointed out that there was a second consistent way to quantize variables, and then there's a particularly interesting thing, which is that the Pais-Uhlenbeck oscillator normally has 2 different frequencies, but this Lagrangian corresponds to the case where those 2 frequencies become degenerate, become equal to one another. In that case, an extra special thing happens, which we point out in the paper from October. I think it's also actually discussed in earlier in Mannheim and Bender's paper, which is that in this limit, if you just solve for the eigenspectrum of the Hamiltonian, of the Euclidean Hamiltonian using the Euclidean norm, the natural Euclidean norm, the Hamiltonian has purely positive energy states. And then also an interesting thing is that the ground state has positive norm, but all of the higher states on the ladder of states are null. They have zero norm. So it seems to be saying something like that only the ground state is physical, and that the fields are really just in some sense correct. My interpretation is that it seems to be hinting that these fields are just somehow correcting the vacuum, so that it has they're just kind of an accounting trick that fixes the vacuum, fixes the vacuum energy, fixes the Weyl anomaly, fixes the vacuum correlations in the early universe, without actually introducing any new physical degrees of freedom, propagating degrees of freedom. But
they're assuming some new quantization, okay? So I think, if I remember correctly, Philip's approach, you don't have the usual bracket inner product, but you define some left-right inner product. So we are assuming that, I think Philip was basically.
That's one way to say it. Yes, yes.
I don't want to interrupt this conversation. It's great. May I kindly and humbly suggest that, because I'm trying to put this on time, and we have 30 minutes discussion at the end of the session to more questions. So unless you object, if you allow me to suggest humbly that you postpone this to the final, to the last item of today's session. And then now it follows Chris Ripken or Ripken. I apologize. I don't know if he's there. I don't see.
Is our first in-person speaker. So.
Okay. I apologize. Great. I was trying to see him on the panel, but it's fine. So Chris Ripken or Ripken, I don't know. I apologize. Is going to talk to us about the Sitter scattering amplitudes in the Born approximation. So here it is. So up to you, Chris.
So let's have a look how this is going in a hybrid format. So let's talk without the mouth mask. That's probably a bit more convenient. Well, hello everybody. I'm Chris, and I'm going to talk about a project that I did recently with my collaborator in Mainz, Renata Ferrero, and it's about scattering amplitudes in the Born approximation, but in the Sitter space-time. So I guess it's just, yeah. So I guess a very famous computation that probably everybody knows in quantum field theory is that when you compute a three-level scattering amplitude and you take the non-relativistic limits, you can reproduce the Yugawa, the Coulomb potential. And this is a very elegant way of showing that quantum field theory is sort of connected to classical physics. But one question that I would like to address in this talk is the question what the Newtonian potential in the Sitter spacetime looks like. So can we set up a computation where we compute a three-level scattering amplitude just like we do with quantum field theory, but then in a curved background, and then have a look what the Newtonian potential actually is. So immediately that raises some expectations. So we know that the Sitter spacetime can be seen as an exponentially expanding universe. So we would like to see some kind of repulsive force. And actually from sort of classical general relativity, we know that you can use the geodesic equation to derive a classical potential, which is the 1/r Newtonian potential that gives the attractive gravitational force. But in addition, there is also a repulsive force that grows sporadically with the distance between the two particles. Now, with these expectations, there are also some questions that arise when we think a little bit about the problem of gravitational scalar scattering mediated by gravitons. And that is that in the Sitter spacetime, you have a non-zero cosmological constant. And that means that the graviton propagator will have something that looks like a mass term. So instead of a 1 over p squared propagator, you will have a propagator which looks like 1 over p squared plus 2 lambda. So one of the questions that I would like to answer is the propagator massless or massive, or whatever the equivalent is in the Sitter spacetime? Then other questions that you can ask yourselves: do you see effects on the Sitter background that the graviton is really a spin-2 particle? And of course, the Sitter spacetime has a very famous horizon. And do we see something like this in the Newtonian potential? So as a little warm-up exercise, I will quickly review the Yukawa potential if you forgot this from your quantum field theory course. So let's take the very simplest toy model to compute the Yukawa potential, that is scalar phi cubed theory. Then you can compute the 3-level 2-to-2 scattering amplitude. And in if you compute this relativistically, this is essentially just lambda squared, which is coupling of the 3-point couplings divided by q squared plus m squared, which is the propagator of the intermediate particle. In order to compute the Yukawa potential, you typically take the non-relativistic limit. So you assume that the mass of the intermediate particle is much larger than the 3 momentum of the momentum that runs through the propagator. And that gives essentially the Fourier transform of the classical potential. So in order to really compute the potential in position space, you take the Fourier transform with respect to momentum. And in flat spacetime, this is a contour integral that you can do. So you take the Fourier transform of the 1 over q squared plus m squared. And what this gives you is a 1 over r potential multiplied by an exponentially decaying function. So this is the Yukawa potential, which is the classical potential associated to a massive intermediate particle. And if you take the mass of the intermediate particle to 0, you reproduce the 1 over r Coulomb potential. So this is essentially the computation that I would like to generalize to the Sitter spacetime. Let's have a look how to do this. Now, I know that there are many problems or challenges to be addressed in quantizing theories on a curved background, but I'm going to be a little bit cavalier here and assume that the sort of standard Feynman diagram approach to computing scattering amplitudes is a correct one. That means that we can start with an action, which will, in our case, be split into 2 parts. So a gravitational action, which we will take the Einstein-Hilbert action as gauge fixing, and a scalar action, which is just a minimally coupled scalar with a mass term. And actually, we will study the scattering amplitude of 2 flavors of scalars, so a scalar field phi and a similarly coupled scalar field chi. As I said, how are we going to compute the scattering amplitude? Well, we are going to compute propagators and vertices from the classical action, and we're going to paste them together in order to form a scattering amplitude. Now, at 3-level, this will consist of 3 parts. So you will have the 3-point vertices, which are called t chi chi and t phi phi, which are given by taking 3 functional derivatives of the classical action, 1 with respect to the metric and 2 with respect to the scalar field. And in between, there is a graviton propagator, which you get by taking 2 functional derivatives with respect to the metric and then inverting this operator. And this, in principle, this works in a curved background as well. So in order to make this a little bit more insightful, let's take our phi cubed scalar theory. Then if you compute the propagator of the intermediate particle, this becomes a differential operator, which is box plus m squared inverted. And this acts on the 3-point vertices which are just the scalar fields themselves multiplied by the 3-point function. But of course, as we will see, this is a little bit more complicated if we compute gravitationally accumulated scattering. So let's talk a little bit about Feynman rules in the Sitter spacetime. And the Sitter spacetime is a very special spacetime. It's characterized by a constant scalar curvature. So the Ricci scalar is 12 times the Hubble constant. And this essentially fixes all the curvature relations that you can think of in the Sitter spacetime. So in this background, how do we compute the propagator and the vertices? Now, the propagator is obtained by taking two functional derivatives with respect to the metric, and then you have to invert this differential operator that you get. And how we do that is we use the defining equation of taking an inverse. So we take S2, which is the second variation of the action. We compose it with an ansatz for an operator that we write down, and we demand that this is equal to the identity operator. What is the ansatz that we use for this? Well, we write down essentially all tensor structures or differential operators that you can write down with 4 indices, or 2 upper indices and 2 lower indices. And this must be multiplied by a function which can only be a function because of the de Sitter symmetries, which can only be a function of the Hubble radius and the covariant D'Alembert. Now, what is the number of tensor structures that this is sort of acting on? Well, this is, so as I said, this is all the different operators that you can write down. So there's, for instance, the identity operator on the space symmetric 2 tensors. You can have a projector onto the trace mode, and there are, I think, 3 or 4 operators that you can write down consisting of metrics and covariant derivatives. So this is how we compute the propagator. How do we compute the vertices? As I said, we compute this by taking functional variations with respect to the metric scalar fields. And this will yield an operator which is written over here. So it can consist of metrics multiplying scalar fields. You can have covariant derivatives, and then you get all combinations. We're going to compute an on-shell amplitude, which means that every time you encounter a box acting on the phi field or similarly the chi fields, you can replace the box by a mass term. Now, how do we compose this in order to obtain an amplitude? We contract the 3-point function with the propagator. So, and this will give us an operator which looks like, which essentially will consist of a number of covariant derivatives acting on the phi fields. I have these form factors stemming from the propagator, and this is contracted again on the other side with the 3-point vertex of the chi fields, and you have to contract all possible indices. Now, in order to bring this into a canonical form, we want to, well, I mean, there are indices mu, and rho and sigma on either side of the form factor. We would like to commute all these covariant derivatives, which are on this side, to bring them to the other side in order to contract them and use the on-shell relation. And luckily, since the Sitter spacetime has a constant scalar curvature and nothing else, we can do all these commutations. So, for instance, if you have a function of the D'Alembert acting on covariant derivative, and then you have a scalar tensor which it is acting on, they can commute this covariant derivative with the function of the D'Alembert, and it will just give you a shift in the argument of the function. And this is a technique that I developed together with Benjamin Knoll, who is also here in the audience, in slightly different context of affine gravity. It's a different story. So with these techniques in place, we can set up, at least formally, the expression that we would like to compute for the scattering amplitude. We can do all the contractions, we can do all the commutations, and this will give a scattering amplitude in the series spacetime. So what does it look like? So the result is, well, it's a number which consists of an integral over spacetime, and it consists of derivative operators acting on all of the support scalar fields. Now, the scattering amplitude splits into two terms, which I've labeled with a T mu nu, which is a function of phi1 and phi2 and phi1 and phi2, and just the scalar fields multiplied themselves. The T mu nu, as you can see, contains two indices, so it's a symmetric combination of the derivatives acting on the two scalar fields. It's multiplied by, of course, the Newton coupling. So these are essentially the coupling constants of the 3-point vertices. And in between these combinations of the scalar fields are non-local differential operators. And what is rather special is that there are these have the form of a propagator, which are dependent on, which have a mass term which depends on the Hubble radius. Kind of rather special properties of this amplitude functional is that it's gauge invariant if and only if the fields plus the background metric are on shell. So both the background metric satisfies the Einstein equation, and all the fields satisfy box phi equals minus m squared phi. If you look at this expression, you might be a little bit worried about the mass terms that appear in the propagator. So in the two derivative part, you have a positive mass. Well, I will refer to this parameter as a mass, but as you will see, that we should be a little bit careful with this. But in the scalar tensor structure, you actually have a mass parameter which is negative. Might be a little bit worried about this, but I should stress here that we are talking about highly non-local operators on the Sitter spacetime. So it's actually a little bit more subtle whether these operators really constitute tachyonic operators. And this is actually a question that I would like to address in the remaining part of my talk, because these differential operators are rather abstract things. They are not really numbers. So in order to really make an interpretation, how should we turn this abstract differential operator into a concrete potential? And in order to do this, we want to compute essentially the distribution of a function of the inversion, which would be like box plus m squared inverse. We want to know how it distributes over the product of two scalar fields. Now, in order to do this, we have to make an approximation. And the approximation that we do in our paper is we take the adiabatic limits. So we define, and in the Sitter spacetime, we have access to a massless parameter, which is the mass of the scalar field divided by the Hubble constant. And we will assume that this is much larger than 1. So essentially, this means that the mass of the scalar field is much larger than the expansion, much larger than the expansion of the universe. In the Sitter spacetime, we can solve the equation of motion for the scalar field exactly. For the solution, we will use the solution in terms of Hankel functions, which essentially is equivalent to choosing the Bunch-Davies vacuum. And then combining this mode function with the adiabatic limit allows us to distribute a box operator on the product of two scalar fields. It will give us to leading order a term which is proportional to the momentum difference of the two scalar fields plus sub-leading terms 1 over the mass. So with these techniques at hand, how do we compute a propagator with a generic mass parameter, which I call Z, which can be expressed into a massless parameter zeta times the Hubble radius for the Hubble constant squared. As we saw from the previous slide, if you act with a box on the product of phi1 and phi2, it will give you a multiplication with a function which depends on eta only. So we are going to make an ansatz that the propagator acting on the product of two scalar fields is also of this form. So you have a function which depends on eta and zeta plus subleading terms in 1 over mass. Also, with this T mu nu operator, you can act on it with a box plus mass squared. And you get more tensor structures that you for which you have to make an ansatz. This will give 7 different functions actually. But you can make a similar ansatz as in the scalar case. So what is now the strategy to compute the propagator? We are going to use the defining relation again for the inverse of an operator. We are going to act with box minus z again on this ansatz that we made. We distribute the box that appears in the local Klein-Gordon operator over the GI functions, and then require that this gives an identity, so that if you act with box minus z on box minus z inverse, that you just get the initial tensor structure again. And this gives you a system of coupled second-order inhomogeneous differential equations. So, for instance, you can see that if you act with this operator on G0 times phi1, phi2, you will get 2 derivatives from the box that act on the G0. So this gives you a differential equation that you have to solve. Now, this was highly non-trivial to do, but we were actually able to solve the differential equations analytically using a power series ansatz. This is also known as the Frobenius method. We require that the solution that we obtain is analytic. And what we then see is that the solution is then a function of eta times q only, where the length of q only. And this I call factor q. And it is reminiscent of what happens in Minkowski spacetime. There also the Fourier transform of the potential is a function of the length of the momentum only. And this indicates that you have a central potential. Now, if we then write down the solution of this expanded scattering amplitude, I will not write it down here completely because it's rather long, but it consists of many hypergeometric functions, 1 f 2. And the result is depicted over here. In the next couple of slides, I will discuss this further. So what do we see from this potential? First of all, if we remind ourselves what the amplitude looks like in flat space-time, we know that it is a 1 over q squared potential. So it has a divergence at q going to 0. And as we see in this plot, is that there is no IR divergence. So this is a sign, I think, as we interpreted it, as the sort of mass-like behavior of the potential of the scattering amplitude in de Sitter spacetime. So the de Sitter, the Hubble constant, will actually act as an IR regulator. If we take the momentum to infinity, we see something rather special that happens, namely that the amplitude actually starts to oscillate, and it actually approaches a cosine rather quickly. Now, we were quite puzzled by this, and we interpreted it, but we observed that the scattering amplitude actually, if you interpret it as a transition probability, we observed that this actually gives discrete momenta for which the momentum transfer, this process happening, is forbidden. And this is quite reminiscent of putting a particle in a box where you actually have momenta for which the transition is allowed. So it's sort of the inverse of this. So this particle in a box-like behavior, we interpret this as coming from the de Sitter horizon. Well, you might be a little bit confused by looking at this picture and say, well, if I take the Hubble constant to 0, I should get back the flat spacetime potential. Does this happen indeed? And that is indeed the case. So if we look at the period of these oscillations, this is proportional. So this is periodic to Q. But if you take the Hubble constant to be 0, then these oscillations become smaller and smaller. And eventually, if you take the Hubble constant to 0, you actually reobtain the continuum. So that is my discussion about the scattering amplitude. Can we now compute the scattering potential in position space? So can we do the Fourier transform as we did in with the Yukawa potential? So in order to compute the Fourier transform, I define a dimensionless radius, which is in the Sitter space-time given by a formal time inverse multiplying the co-moving radius. And if we take the Fourier transform with respect to this dimensionless radius, we can indeed obtain the classical potential. So again, I'm not going to actually display the entire formula here because it's rather complicated, but it splits into two parts depending on whether the radius is smaller than 1 or larger than 1. And I should note here that this radius is actually, so it's because it's in dimensionless units, it's expressed in Hubble units. So r equals 1 is actually exactly at the Hubble radius. Below the Hubble radius, the potential is non-zero. It consists of a rational function and a bunch of hypergeometric functions, but this time not 1 and 2, but 2 and 1s. And above the Hubble radius, the potential vanishes analytically. And again, I have depicted here on the right the potential. So next couple of slides, I'm going to discuss the different features of this potential. So first of all, you see that there is this curve here. So in order to get a bit of an analytic feeling of the potential, we did an expansion in around 0 radius. And when we expanded this, this was the expansion that we got. So the leading order term is a part of R term, well, a constant term, and then a term which is linear in the radius. And the dotted blue line here in the picture is actually this approximated function. And we see that this function is rather good. So in the plot below, I've plotted the residue of the function, and you see that the values are really rather small. So the leading order term is a 1 over R term, and this is actually completely consistent with the classical Newtonian potential. So at small distances, we really reproduce the classical Newtonian potential. However, if we make the radius larger and larger, we see that the linear term becomes more dominant. And if you sort of interpret this potential as a classical potential that gives rise to Newtonian force, this coefficient, because here it is negative, it will give rise to a plus sign of force. So actually it will yield a repulsive force at large distances. We interpret this as consistent with the Sitter universe actually modeling an expanding space-time. So the repulsive force is actually a sign of the expansion of the universe. What is rather striking here is that this potential is very different from the geodesic potential that I depicted on the very first slide. But if you think about it, this is actually not super surprising, because the geodesic, when you use the geodesic equation to derive the potential, you actually assume that the particle that is moving throughout space-time is a light test particle. And this is, of course, completely at odds with the heavy mass approximation that we did in order to compute the adiabatic expansion. So actually what we are looking at and how we are interpreting this potential is actually that you have two very massive masses inside of the Sitter universe. So it's more like a double black hole geometry, for which, as far as I know, not many exact solutions exist. So that is the discussion about the small distance behavior of the potential. Let's go and have a look now at the large distance behavior. So we see that when the dimensionless radius exceeds 1, the potential drops off to 0 exactly. And that is quite dramatic behavior, but it's actually completely consistent with the expectation of the de Sitter horizon. Because if you have two particles that are separated by more than a de Sitter horizon, then they cannot have causal interaction anymore. So therefore, the gravitational force between them must be zero. So actually, that the potential drops to zero analytically is a rather nice feature, I think. Also, because the potential is now has a bounded support at large distances, it means that if we sort of want to integrate over the potential from a finite distance to infinity, this integral is actually finite. So this is again a sign that there is no infrared divergence. If we now look at the residue plot here below, we see that there is a discontinuity in the potential. And well, this is, I think, one of the most puzzling things of, or one of the most puzzling results of our work. How do we interpret this discontinuity? And we have come up with a couple of ideas what this could mean, but this is still very much ongoing work. One of the things that we were thinking of is that we could make an analogy with electrodynamics. So if you have an electric potential with a discontinuity in electrodynamics, this is typically associated with a surface energy density. Well, that would be the gravitational analog here, or in electrodynamics, it's a charge density. The analog in gravity would be a surface energy density. Another thing that came to mind is that when you actually interpret this potential really at face value as a classical potential, and you throw in a particle in this potential, that when it hits this discontinuity at an impact angle which is large enough, then it will actually be reflected by the discontinuity. So particles that hit this discontinuity that are inside the Hubble radius might actually be reflected again into the Hubble patch of the universe. So this is still ongoing work. We are trying to figure out what this means. Another thing that you could think of is that the de Sitter universe is expanding, and that at the Hubble radius, the de Sitter universe is actually expanding faster than any particle can fly out, so that you get sort of a shock wave, because the universe then, the speed of propagation of the universe is actually exceeding the speed of propagation of the particles. Another thing that would be incredibly interesting to investigate would be if you treat this potential in a WKB approximation, and you study tunneling of particles to this potential. This might actually be connected to a thermodynamic description of this discontinuity. So I think I'm actually rather good at time, but let me summarize quickly. So we have seen in this talk how to compute an amplitude functional on a de Sitter background using functional commutator relations in order to contract derivatives. We've seen how to compute from this rather abstract differential operator description a concrete amplitude and a potential using a large mass limit, a geometric limit. And this allowed us to distribute the propagator acting on products of fields. This gave rise to a rather interesting scattering amplitude, which contains no infrared divergence, and in momentum space had these interesting oscillations. And in position space gives rise to repulsive force at large distances and an analytic vanishing outside of the de Sitter horizon. So this is still rather ongoing work. What is next? Well, in this work, we computed the scattering amplitude to leading order in the dimensionless mass. So can we compute the expansion next to leading order in 1 over the mass? Well, there we actually have to distinguish between in which masses we are expanding. So if you have the mass on which the differential operators do not act, we can quite easily compute the next to leading order. This will give rise at least to sort of angular dependence of the scattering amplitude. So the next to leading order will not be just a central potential, but it will actually depend on the scattering angle of the two particles. You want to go next to leading order in the particle mass where the differential operator do act on. We get a new set of propagator differential equations which we have to solve. And this is rather hard. Now, another extension that we could think of is to compute the scattering amplitude with non-minimal coupling. So for instance, you can go to higher order in curvature, so Ricci scalar square coupling or wild tensor square coupling. Or you can introduce non-minimal couplings between gravity and the scalar fields. Well, this we are actually actively working on, and we hope to publish our results on this soon. But a striking feature that could happen is that these couplings give rise to a new scale compared to the Hubble scale. And this will also give rise to corrections into potential. And it would be very interesting if this could give an explanation or at least a connection to modified Newtonian dynamics or an interpretation of dark matter. Now, I've only talked about the three-level scattering amplitude in this talk. So in principle, we can only discuss first quantized effects. But if we want to compute second quantization effects, we have to include loops. And it will be very interesting to compute, to see whether there are large-scale effects due to these quantum corrections. Well, in the past, I've been involved in a collaboration producing an elegant way to compute or just to characterize all these loops. And that is by means of a form factor language. So that uses the quantum effective action to parameterize all the quantum corrected interactions. And it would be very interesting to do this on a de Sitter background. Then your quantum effective action contains form factors to incorporate all the momentum dependence of the vertices. So this will give rise to functions, not only of the covariant momentum, but also the de Sitter or the scalar curvature. And if we compute this gamma either perturbatively using a Trace-Walk formula or generalization level, or non-perturbatively, we can compute the quantum corrections to this action and therefore also the quantum corrections to the scattering amplitude. But this is still ongoing work, so I'm very excited to see what comes next. Now, with that, I would like to end my talk and thank you for your attention.
Thank you very much in the precision time. Thank you. So Philip Mannheim has raised his hand. So Philip, please.
Yes, Chris, thank you for this talk. I wanted to comment on the degree to which the de Sitter parameter H actually appears in propagation. Now, you discussed massive scalar fields, and then everything goes the way you described it. But if the scalar field were massless, the question you can still ask is, does H still act as a mass? And the answer is, it depends on the nature of the scalar field wave equation. If the scalar field wave equation is conformally coupled, because the de Sitter geometry is conformal to flat, you can make a conformal transformation to flat for everybody, and then the propagator is only on the light cone. However, if you have a minimally coupled scalar field propagating in a de Sitter background, then you are off the light cone and you do get a sensitivity to H.
Yes.
Yeah.
Yes, that's absolutely right. So in the work where we include non-minimal couplings, so this R55 coupling, we can exactly pinpoint this conformal point. So we can take the bare mass, if you wish, to be 0, and then the R55 coupling to be 1/6, and then indeed we should be exactly at the conformal theory, and it is massless for any observer.
Yeah, very good.
Thank you. Any further questions?
We have a question here from the audience.
Yes.
Maybe I can do this.
Where? The audience, I apologize. Yeah.
So thanks for your talk. Can you elaborate more what are the conditions for suspension of this mass? Because let me say, you can imagine the situation that they are just three masses and you let them go, the space-time evolves and the masses can drift away. Or you can imagine that they are like we do this typically theoretically with black holes. That you take the mass and then you put the rocket engine and then you say, okay, it's a stationary particle because So can you say more which kind of conditions you put for these masses?
Yeah. So my interpretation is really as if you want to interpret the potential, it's really a classical potential as you would use it in classical physics. Sure. So you can use it to compute orbits and things like that. So what would be interesting here is if I want to sort of connect to your stationary points, is that the potential has a critical point here. It has a maximum. So in principle, at this point, you can have a particle which is stationary there. It will stay there.
Yeah, the force of zero.
Yes, exactly. So if you are inside this, and this is almost exactly at half the Hubble distance. So if you subtract this the approximation, it is exactly half Hubble radius, but this correction gives a slight correction to it. If you are inside this regime, then you're experiencing an effective attractive force. So you have circular orbits, or if your energy is large enough, you can have hyperbolic orbits. But if you are at a distance larger than half the Hubble radius, then you're actually experiencing a net expanding force. So if you are then a particle which has zero initial velocity, you will actually drift outwards.
Yeah, but I think that it's not the case. It would be because of the overall expansion of the space. Yeah, I mean, this is
yes.
But I think that this is my comment that, as I understand in your computation, you took this particle as a free one. So I mean, you do not attach any additional force. Like I said, you can put the rocket engine on each of them. In principle, in a general situation that you are in third space-time, you can really also study the situations here that you would say like both observers, one sitting on one particle, another sitting on the other, they thought about themselves to be stationary. And then you can consider what's that amplitude, because of course the computation typically like we do in flat space and we do not distinguish whether there are free particles or whether they are stationary observer particles. But here, of course, on a general curve background, it makes a difference. And then you would probably get a different amplitude, different potential, even if you take this case that they are the rocket engines.
Yeah, so I think actually that there should be a mapping between those two pictures. So if you have the scattering amplitude as it stands now, you have two free particles that enter the scattering process. They exchange a graviton, but this time on a curved background, and they fly away again. So the interaction with the background, sort of the external potential, if you wish, that is now encoded into the vertices and into the graviton propagator. So if you want to make the point of view that you are on one of the particles and you have a rocket engine, then you sort of have to do a coordinate transformation or something more general than that in order to take this effect into account.
Well, thank you. I think Sravan has a question. Sravan?
If there is time.
Yes, please.
Hi, Chris. Thanks for the nice talk. I have a very short question. So you took some massive scalar fields. You took the masses to be higher than the Hubble scale. What if you start with some ghost-like scalar field, and how your result changes?
That is a good question. So I think what will happen here is then your expansion in terms of these Hankel functions will change character. So if the mass is very large and positive, the Hankel functions are actually sort of oscillating. And to a good degree, they are actually approximating the Minkowski space complex exponentials. However, if you make the masses negative, then this changes character rather drastically. I think they're not normalizable and things like that. So that might be a bit tricky to interpret. And in any case, if you want to make the masses rather small, it is difficult to, well, you cannot do the adiabatic expansion anymore. So if the masses are small, then it will be hard to turn this abstract differential operator description into a scalar function.
Thank you.
Okay, thank you.
Thank you. If there are no, I see no one else. So I would then ask.
Question, I think there is.
Oh,
if
there is someone on the audience?
Yes.
Oh, okay.
Thanks for the nice talk, first of all. So I was wondering if you elaborate on what grounds we can actually call these quantities sampling amplitudes in the standard sense because of the problem with asymptotic states.
Yes. Yeah, that is a good question, and therefore I gave this little disclaimer at the beginning of this talk that this is actually rather an unsolved problem because you cannot have asymptotic states in a de Sitter background because there is always curvature. So as far as I know, this is not a solved problem. So we took the point of view that we do not take this into account at this moment and just try to compute something which is at least as close as possible to the Minkowski space scattering amplitude. So I think at this point it's hard to make any concrete statements about this. Thanks.
Thank you. So any more questions, either in the audience where I cannot actually see if anyone raises his or her hand, or in the Zoom audience, say on the clouds, where people raise a Nikon hand and I see them. So if not, we will proceed. And now it's the time for Artem Starodubtsev, if I have said your name correctly, I hope. If not, I ask you to apologize me.
Okay.
And Artem is going to talk to us about quantization of gravitating point particle and the spectrum of quantum space-time. Artem, up to you now. Thank you.
Thank you. Can I? Oh, okay.
I see you and I hear you.
Okay, you hear me? Good. And here is a presentation. Okay.
Right.
Well, oh.
It's okay. We are seeing.
Yeah, you see me, but I don't.
And I see also the screen. I see the first slide.
Okay. So this is about quantization of a model, maybe a kind of mini superspace, which includes gravity, but in which all but a finite number of degrees of freedom are frozen. So this is quantum mechanics rather than quantum field theory. And so the model which we will study is a point particle without gravity. It's very simple, we know it. Here is the action, Poisson brackets, standard mass shell condition, and quantization is standard. And now we try to see how this is going to change when we include gravity. By including gravity, we mean not placing this particle in external gravitational wave, in external gravitational field. This is a well-studied model, but we take into account gravity created by this very particle. This is a sort of Ptolemaic point of view. So we study massive particle and light test particle whose gravitational field can be neglected. And we associate the rest frame to the light particle. So light particles stay fixed and a heavy particle moves. And we will study, so the degrees of freedom of this particle will be again translational, how it moves around the space-time. And importantly, the test particle will be at a finite distance of a massive particle. Otherwise, at an infinite distance, it will be all trivial. So this is, so let's consider action for this model. First, this is gravity action taken in Einstein-Cartan formulation, where the variables are tetrad field and Lorentz connection. This action is invariant with respect to local Lorentz transformation, gauge group, and also with respect to four-dimensional diffeomorphism. So because we don't know well how to work with finite diffeomorphism, we consider in this model infinitesimal diffeomorphisms which act on fields locally. And this is, of course, a severe limitation of the model, but at least something to start with. So these are diffeomorphisms. And the second term on the right-hand side on this can be considered as infinitesimal gauge transformation. So the second terms on the right-hand side, in fact, could be neglected. Could be because could be included into gauge transformation. And let's add to the gravity action the action of particle. Particle we consider spinless particle. It will be as a point source in the case of, in the absence of spin, of a metric field. In this form, it is not, it changes with respect to gauge and diffeomorphism transformation, and those gauge and diffeomorphism transformation at the location of a particle become its degree of freedom. So this is the way the action transforms under gauge and diffeomorphisms, and we, as a result, we get this invariant coupling of particle to gravity plus kinetic term of the particle. So the parameter of diffeomorphism transformation will play the role of canonical coordinate, and gauge transformation via form a coadjoint orbit of Lorentz group, and this coadjoint orbit plays a role of momentum. So this momentum automatically satisfies the mass shell constraint, and the kinetic term for the particle is standard. So this is indeed the action of a particle. But now what happens if we combine it with gravity? Also, in the gravity action, we have to include boundary conditions. We will divide our space-time into two regions, one containing the heavy particle and the other test particle. Why we do so? Because in each of this region, we will have a static solution, a solution which is static, time independent. So we can choose the rest frame of each particle in each region. If we have both particles in one region, we wouldn't have static solution because they obviously move to each other. So the boundary is placed between a heavy particle and a test particle, and on this boundary there is also contribution to the variation of the action due to flipping the derivative. And there is also a boundary equation of motion, apart from bulk equation of motion. And if we don't add any boundary term, then the boundary equation of motion means that metric is totally is degenerate, so it is incompatible with bulk solution. But we can add boundary term. This is not Gibbons-Hawking boundary term, but this is a boundary term of such type that the resultant boundary condition will be such that they impose no restriction on physical degrees of freedom. They can be satisfied just by choice of the gauge. And indeed, if we combine the variation of such boundary term and bulk term, we have the following boundary variation, which is satisfied if zero component of metric is equal 0 and zero component of connection is equal 0, which in particular is satisfied on a horizon of a black hole or on any horizon in a static gauge. So now with this boundary term, we take the constraints, solve them. Well, we choose the solution, which is static and spherically symmetric. This is basically Schwarzschild solution, and take it into an arbitrary gauge and plug it back into the action. It turns out that the bulk action of gravity and the contribution from the particle action, kinetic particle action, are all cancel out. All cancel out, and all that remains is a boundary term, is a term on the boundary, which depends on the gauge and diffeomorphism parameters. This is very analogous to Wiedźmina-Witten action in 2+1 dimensions, where it appears as a boundary term for Chern-Simons theory. Everything in the bulk cancels out, but instead we get action on a boundary. So same story is here, but it's a three-dimensional action. But of course, our model is with finitely many degrees of freedom, but here we got the full field theory on a boundary. So there are too many degrees of freedom, and we have to find out what to do with the rest, how to extract from it the finite number of degrees of freedom we are interested in. So this is a Schwarzschild solution, which we plug it in as a background solution. It includes the familiar expression for the lapse function, and also it includes some normalized three-dimensional vector field on a two-sphere, which subject only to conditions that it has a unit norm and it has winding number 1 on a sphere. Otherwise, it could be arbitrarily deformed, continuously deformed, such that these conditions are satisfied, and this is still the solution. Well, example, if we take a spherically symmetric configuration, then this field is so-called hedgehog. It's a field normal to the unit sphere. Now, what we have to do, we got boundary term from inner region and boundary term from outer region in which the test particle is located. And now we have to combine them. In order to combine them, we have to apply continuity condition of metric and connections. So the background field is the same, and this is condition on the gauge parameter inside in inner region and in the outer region. And so the condition of continuity of metric and connection results in that the gauge parameters and diffeomorphism parameter must differ from each other by a quantity which are covariantly constant. But covariantly constant, because we have non-zero curvature on the sphere, this have a compatibility condition of covariant of being algebraic condition, which means that it commutes with curvature. And this condition is too restrictive. What we can do to weaken this condition is to use that freedom in the choice of field on a sphere, normalized field on a sphere, which enters the Schwarzschild solution. So we can start with spherically symmetric configuration, but we can continuously deform this field, and this continuous deformation map a solution to solution. This is, however, not a gauge transformation, but it could be shown, but it's in infinitesimal form. It coincides with diffeomorphism transformation. So let's cut our sphere, our boundary, into hemisphere, and on one, and at each hemisphere, we can put this field to constant, so-called comp the hedgehog, and then curvature on upper and lower hemisphere disappears, and all that remains is the curvature at the equator. So it will consequently allow us to reduce the action to the equator after, so we can solve the condition of continuity of metric and connection, which means that those fields which connect gauge parameter outside and inside are just constants. And when we add these two terms from outside and inside, we find that the action on lower hemisphere and upper hemisphere cancel out, and we have action reduces to action on the equator. But this is still a field theory. Let me now use a further simplification of the 4 degrees of freedom for momenta and for coordinates. Fix one coordinate and momenta, meaning that particle would move on in a plane, which is basically compatible with classical dynamics. In this case, the above action can be and using our approximation, the above action can be reduced to purely mechanical action. This is no longer a field theory, where psi is a background, psi bar is a background field whose covariant derivative is a background metric, and psi is now diffeomorphism. This plays a role of particle coordinate with respect to and the remaining part is holonomy of a gauge group around the equator, and it will play the role of momentum. One can show that this holonomy will satisfy has a fixed conjugacy class, whose basically this is a constraint, whose where the value of this conjugacy class can be derived from the solution of Einstein equation just by calculating the holonomy of the connection around the equator. And from this action, we get Poisson brackets from which momenta commute, momenta are commutative, coordinates, but momentum is group value. This is an element of SL2 group. Now, coordinate acts as left invariant derivative on this group, and coordinate have non-trivial Poisson bracket between themselves. They commute as SL2 algebra element. And this commutator also, one can see that they decay with a distance away from the particle. And there is, of course, this constraint equation, which is fixing conjugacy class of U. So this is momentum space. Here we depict only temporal and radial coordinates. Yes, has this form of this hyperboloid. And the constraint has the following form. One can show that in the limit of small gravity of Newton constant goes to 0 or radius goes to infinity, this constraint becomes p squared equals to m squared, standard particle mass shell constraint without gravity. Graphically, the solution of this constraint can be shown by section of a plane, of section of this hyperboloid by a plane. There are two. If distance between test particle and heavy particle is larger than Schwarzschild radius, we have the following solution of mass shell constraint, which looks like mass shell of ordinary particle. And when radius is smaller than Schwarzschild radius, the solution of the constraint has looks like a mass shell of the tachyon. And these 4 branches of the solution to the constraint can be identified with 4 regions of Penrose diagram.
Did you say 5 minutes?
Yeah, 5 minutes. So the above ordinary particle is left-hand side and right-hand side of Penrose diagram, and then so outside of a black hole, and inside the black hole, these are these tachyonic branches, upper and lower sectors of the Penrose diagram. And now we can quantize this model. Of course, this is just quantum mechanics. We want to define our wave function on the entire momentum space. It is convenient to use momentum representation, and the global coordinates on momentum space are provided by Euler angles. There are periodicities, well, in a variable which plays the role of energy and with actual angle. So scalar product uses the Haar measure on a group. And so let's consider coordinate operator. First of all, operator of time. It is a derivative with respect to variable on which we have periodic boundary condition, which means time is discrete, has discrete spectrum. And also we can calculate the spectrum of invariant distance. So it will be a Casimir operator of SL2 algebra. There are, if we take, if we allocate it at a distance larger than Schwarzschild radius from a massive particle, then the spectrum, the interval is space-like, and the spectrum of space-like interval is continuous, but bounded from below. On the other hand, if you take time-like distance to the horizon, which happens inside the black hole, the spectrum becomes discrete. And here are the eigenvalues. So the distance operator between test particle and heavy particle has discrete spectrum inside the Schwarzschild radius. And the distances between the eigenvalues are they increase as we go closer to the center of the black hole. So this is the radius downstairs, means that as we go from the horizon to center of the black hole, the eigenvalues become scarcer and scarcer, although our approximation, where we use infinitesimal diffeomorphism, it only works in the neighborhood of the horizon. So to go deep inside the horizon, we need to go beyond this approximation. Although in 3+1 dimension we cannot do this, at the same time, in 2 days from now there will be a talk by Alexander Andrianov on similar project in 2+1 dimension, and there we can calculate the spectrum of distance operator all the way to singularity. So spectrum is continuous outside of black hole, discrete inside, and the distance between eigenvalues increase from the horizon towards singularity, which means that possibly there will be regularization of singularity if we be able to calculate it all the way down to there. So thank you. I finished.
Thank you very much.
So
yeah, I think Paulo, our chair, has some problem with connection. So is there any question, either here from the audience or from Zoom?
So
I didn't see any. If not, yes, we can thank Artem for this talk, and we can move to the discussion session. So thank you, Artem.
Thank you.
Okay, I got a message from Paulo again. So he says internet is down. He's trying to connect.
So okay, I think Artem can also stop the screen sharing. It's down. You can stop it.
Okay.
Oh, stop. What's this? What's this?
I'm sorry, my internet kept very unstable, like a strange attractor, and I'm always taking refuge in the assistance of my kind friend Sravan Kumar. I apologize. So any further questions to Artem, or were there any questions during my blackout?
No.
Okay, so if there are no further questions, and we are on sort of on time, so it's now the in sequence as we follow. We now go to the let me just try to visualize here, putting everything correctly. We now go to the discussion session, right? If maybe I'm
yes.
Am I down again on the internet, or?
No. We can hear you perfectly.
Okay, it's like circling the moon, you know, like when you go to the dark side, you are without transmission. So I'm just circling very fast on the dark side of the moon. So I'm just a joke. Okay, so now everybody asks everybody, or at least somebody, about the session number 1 and session number 2, right, Sravan?
Shall we? I'm wondering, shall we wait take a 5 minutes break and start the discussion session?
I'm fine. It's up. You decide.
As per the schedule, so we take 5 minutes break. Is it? Yeah.
It's fine.
We'll start in 5 minutes.
5 minutes. Take 5.
While we're on break, I missed the beginning because it was 5:30 in the morning where I am. But I wanted to ask, how many people are actually in Portugal for this conference? I don't know whether you discussed it.
10
people.
Around. I don't know. I cannot specify, but
I can show you. We have 9 speakers actually.
Because I suspect that they're the people that we've been seeing with Luca. Yes.
Yeah.
Okay. Good. And are they all local Portuguese?
No. Actually, no.
Only one. I guess is João Marto is the only one.
All the world. Well,
only one Portuguese. So we have Manuel Asorey here. Okay. Then Ilya Shapiro.
Oh gosh, yes.
Yeah, sorry, maybe I can, well, it's not the best.
Okay, you've just explained to me why Ilya is speaking so early.
Then we have Lucas Maldone, Chris Ripken, Benjamin Nor, Alessia Platania, Ivano Basila, Anna Tokareva, Leslav Rakwal, Joe Marto. Okay. And then, yeah.
Very, very nice. Well done, all of you.
So
I
take
hope
5,
next
right?
time it will be completely offline.
And in presence. Okay, so now as suggested, and I think it's just take 5 minutes just for a cup of tea or whatever. I'll be here in 5 minutes. I'll just, but I will leave the Shravan, are you there?
Yes, yes.
Hi, Shravan. Hi, hello.
So we can, yeah.
So you let me know when it is. I think it is time. So
if we can start. Yes.
If I add properly the 5 minutes where we left, it's now. But yes. We can wait 1 or 2 minutes. So that's not a crucial.
We can start, I think. So
okay. So
I hope everyone is back. Speakers who
we have about 1, 2, 3, 4, 19, not quite 20. At least I see it on the panel on this matrix. But we are around 20 here, and then 10 more in the room. So it's already a fair number.
I think maybe can I start with a question to?
Yes, please go, Shravan.
So, I would like to ask this question to David Wands, if he.
Yeah, I'm here. Hi, Shravan.
Hi.
Sunny Portsmouth.
Yes, still sunny. It is not sunny now.
No, I have a couple of questions, especially on primordial black holes and the stochastic inflation. So one question is about when you said to produce primordial black holes, we need some specific features in the inflaton potential. So, but is it fine tuning? Like, can we how feasible it is to get it naturally from some particular theory, which is some connection with UV completion?
Yes, I mean that's a good question and a topic I didn't get into. I think I was interested in formulating the problem in stochastic inflation, but then the example I gave particularly was quadratic inflation, and that's an example where, I mean, you could produce interesting numbers of large fluctuations, but the only parameter you have in the quadratic inflation model is the mass of the inflaton, and there you would have to have the mass so large that it's, well, the model's already incompatible for various reasons with the CMB, but in fact the mass, in particular the fluctuations, the typical fluctuations, would also be too large. And although there will eventually be this deviation from Gaussian statistics, that's an example where if you have a mass of something like 10 to the minus 5 in, is that right, in Planck units, that would give you the right sort of amplitude on CMB scales, it would also give you an unobservably small number of primordial black holes, and the exponential tail, the deviation from Gaussianity is so far into the tail, it's already, the probability is already way too low. So typically you will, so what people typically do, of course, is have models which have small fluctuations in the large scale regime, but then they have a feature in the potential on small scales. Now, I think our calculation suggests that when you get into the region of these features on large scales with larger amplitude fluctuations, then the calculation is more complicated, than has been done so far. But nonetheless, there will still be this, I think, a fine tuning, whether it's as, we really just haven't done the calculations in realistic models like this to see what the extent of the fine tuning is. But there is still you're still very sensitive to, you're still going into the tail of an exponentially suppressed tail of the probability distribution that will be very sensitive to the parameters that you pick. So I can't pretend, personally, I don't see a reason why that is. I can see that why it would be natural to produce just the right abundance to make the required abundance today, but it's something to be investigated. And if it may simply be that there's a constraint on such models that that indeed you have to avoid going into the regime where you overproduce primordial black holes. That will always be a constraint on such models. Yeah. So, but being just at the boundary in the tuning of parameters that it's of interest is that the abundance is interesting is very difficult. I think is always going to appear fine. Require tuning.
And if I understand correctly from your talk, so the current status is you're actually developing techniques to exactly solve this equation in the non-perturbative regime. So
yes, that's right. Yes, as you get into the regime where you have significant stochastic diffusion, that's right. Which is an interesting regime to study. And the argument I think is that in an extreme case like black holes, we know it's important. It will be interesting. I'm also interested in whether there are other astrophysical cases where it might be significant as well. For example, we know people have proposed in the past using the abundance of high redshift, large clusters, supermassive clusters of galaxies at high redshift, how likely are events like that in the primordial density field. These are the sorts of questions which potentially you could investigate in this framework.
Okay, I have got another question in relation to this. So usually in the standard inflation, we have small quantum fluctuations and we quantize them choosing a particular suitable vacuum, which is Bunch-Davies. But if you have large quantum fluctuations, which are quite larger than the classical background, as you explained, how do we understand quantization? How do you quantize such?
Well, we're not. Yeah, so I'm not doing anything other than the simplest Bunch-Davies vacuum for a weakly coupled field in quasi de Sitter. But you can still have large fluctuations that are large relative to the classical background evolution. And the sort of a classic example of that would be indeed in a de Sitter or a very flat potential. There's nothing bad about in the sense that there's no problem in that sense with having a very small slope for an almost constant potential, and then studying the fluctuations of a weakly coupled field in that background. Of course, what's happening can be that the classical evolution is becoming small, but the density perturbation in that case, associated with the scalar field fluctuation is still small because if you just estimate the density fluctuation as the derivative of the potential times the field fluctuation, well, as the derivative of the potential goes to zero, that density fluctuation, in fact, is becoming vanishingly small if we put a vanishing gradient there. So, in fact, it's still a smooth background in which to study the field fluctuations, and they then become, the reason they can give large density fluctuations later is if you study the fluctuations in the expansion history to a fixed surface, such as a fixed field value that marks the end of inflation, then you can, and then you have reheating to a radiation-dominated universe, and then different regions of the universe can start reheating in effect at different times. So you get this large relative perturbation between these regions. But at that stage, the regions are causally disconnected now outside the Hubble horizon at that time. So again, there's no large perturbation, and indeed you only see the large perturbation as modes come inside the horizon, at which point then you would have to start doing the numerical relativity modeling of the large density perturbations collapsing to a black hole or not. Yeah.
So it's basically the effect of the background is reducing, so that's why the difference is higher. So that's
yeah. So inflation is very good at smoothing out the perturbations for a local observer. As Alexei was saying, it doesn't mean there aren't large perturbations on the very large scale, but until they come back inside the Hubble horizon, then they needn't be dangerous in that sense.
Okay. And for producing black holes, the one scenario you explained that with some features in the potential, there is another mechanism I'm reading recently with multiple fields. For example, in the R² Higgs inflation, there is some way to produce primordial black holes. I don't know the details, but do you think that is much more natural? And in that case, how do we understand perturbations? Because as you explained in your talk, is with single field setup. But if we have multiple fields, the
delta n set interpretation of the density the origin of the density fluctuation after inflation as originating from a perturbation in the expansion history during inflation applies beyond the single field setup. So that carries over that's a very general result. So that applies in a multi-field setup. So that's perfectly applicable. Indeed, you can apply it with non-minimal coupling if in calculating R² inflation, for example, or R² with additional fields. So that calculation can still be done. I think you probably still have, again, to get the right abundance of the very large fluctuations is going to be a delicate balance, I think, in any model that I know of.
Okay, interesting. And well, it's not a question, but I want to know your opinion. Normally in cosmology, people who study at the universe cosmology, primordial black holes is a very interesting scenario. But people who are interested in black holes, there are several questions which are totally unclear. For example, Hawking radiation or unitarity violation, page time. So there is a huge section of people working on need to understand it from quantum gravity point of view. But on the other hand, in the early universe cosmology, we assume the standard Hawking calculation and the time the black holes evaporate, the time that black holes take time to evaporate. I mean, we put some constraint like primordial black holes. If this is the mass, they might have not survived today, so they cannot be dark matter. So this is assuming the standard calculation of Hawking, but there are still so many open questions. So I feel that there is some bridges missing here. How do we connect it?
Well, yeah, I mean, I think, the sort of standard constraints come from assuming, yes, as you say, well, first of all, of course, the classical behavior of black holes, if they're much larger than 10 to the 15 grams, and we can neglect, the temperature, Hawking temperature is low enough. There is an assumption that those are just effectively classical black holes that will survive the lifetime of the universe and beyond. So, and that's probably not going to change according to your different, studies of quantum behavior of black holes. That would only apply to the small scale black holes. I guess the big question is the ones that evaporate. If the evaporation is complete, I mean, the sort of constraints was showing, or one would often be just talking about radiation from the final evaporation of black holes. I mean, again, most of that is occurring when the black holes, most of the energy released is still when the black holes are much bigger than the Planck mass. So again, I guess one assumes that the sort of semi-classical Hawking calculation will work, for black holes much larger, as long as they're much larger than the Planck mass. So the subtleties apply to the final end point of that process, maybe. And so a big question is whether there's, for example, if there's a relic left when the black holes evaporate, a Planck mass relic would indeed give constraints on the existence of large numbers of very light black holes at early times if you still had stable relic and Planck mass relics from the evaporation process. And that again would mean that you would have a reason to suppress the existence of the abundance of very light black holes in the early universe if they did indeed evaporate and leave stable relics. So, but that's the only case I'm aware of. I don't know if others are aware of other implications of different interpretations of black hole evaporation for the astrophysical constraints.
Right. On the audience room, any questions from somebody to anybody, or just somebody? It sounds like making a tune here. Anyone else on the internet cloud, so to speak, that wishes to put some questions, some comments, some challenges?
For Nathan.
I hear some.
Can you hear me?
Faintly.
Okay, I'll speak up a little bit. I have a question for Nathan. So I was wondering what are the necessary conditions for a CPT invariant vacuum state to be unique?
Did you got that, Latham?
Yes.
Oh.
So, well, the first thing to say is that, yeah, so if you have FRW symmetry, ordinary FRW symmetry plus time reversal, then there are these CPT symmetric vacua. Now, they're not unique. It's a bit like in inflation where there are the alpha vacua, but there is, like in inflation, there's a continuous family of de Sitter invariant vacua, but there's a preferred one, which in some sense, the normal Bunch-Davies vacuum, which is least excited. So it's actually very analogous to that there's a family of these CPT symmetric vacua, but there's a preferred one which is least excited according to a late time observer. So that's that in various ways you can show that that's kind of the preferred one in the class, quite analogous to Bunch-Davies. But all you need is that it's FRW plus an overall global time reversal symmetry.
And does this satisfy the Hadamard condition, this preferred vacuum?
I couldn't hear that. Say that again. Does it satisfy what?
It satisfies this least excited condition for a late time observer. Is this the same as the Hadamard condition?
Is it Hadamard, did you say?
Yes.
Yes, it is. Yes.
Okay, thanks.
Any more questions? I don't know if it is feasible, but in the conference room or in the where the people that are locally assembled, if there will be a microphone that could swing, it will be perhaps easier. This is just a suggestion. I'm just so Philip has raised his hand. Hello, Philip.
Yes, I wanted to comment on something that Latham said, and also something that Luca raised in the session this morning. Very quickly, the work that I did actually with Carl Bender, we used PT symmetry, but actually it was CPT symmetry because we're working with the gravitational field or scalar fields, which is C even. So in effect, we really have a CPT invariant theory, and we have a CPT invariant vacuum. And so it may have more connection to your work, Latham, than I had anticipated this morning. And I wanted to comment on that. Now, the other issue that Luca raised was what Latham and Turok have done is they've used an action which is phi box squared phi instead of phi box phi, the standard one. And that one has its fourth order. And so there's an Ostrogrodsky problem. If I can be allowed a very quick screen share, I just want to comment on how it arises and then how it gets resolved. Is that within the bounds of the discussion?
Yeah, sure. Your co-host now. You can.
Okay, good. I'll try to be quick. That one, I think it is. Yes, sure. Okay, yes. So I think so. This is the fourth order theory, and there's the acceleration, the velocity, and the position, and this, of course, is the famous problematic minus sign, which suggests there might be a ghost. Now, if you take that theory, you can simplify it by just dropping the space, by fixing the spatial dependence, and then it becomes what's called the Peiss-Uhlenbeck oscillator theory that Peiss and Uhlenbeck wrote down in 1950. Now, again, you have still the same problem with the minus sign, but what's interesting is if you calculate the Hamiltonian, and this is what Aaron Davidson and I did using the method of Dirac constraints, is you see that you get a term here minus z squared. And that minus z squared in the classical theory is the Ostrogrodsky instability, because it's like a harmonic oscillator with the wrong kinetic energy, and the energy is unbounded from below. And that's the naive interpretation of the theory. Now, what you can then do is you can still introduce canonical quantization operators, A's and A daggers, and you discover that one of the commutators is positive and the other commutator is negative. So you have two choices. The choice that will give you the Ostrogrodsky instability is to take the second one to have it annihilated by A2 dagger, because then A2 dagger becomes the annihilator, and then the minus sign goes away, and everything is positive, but the energy is unbounded because of this minus sign here. So that's the Ostrogrodsky instability. The alternative choice was to take A2 to annihilate the vacuum, then the energies are positive, but now you have the negative energy, the negative norm sign, and then you have ghost states with negative norm. So those were the two options that the theory has, and they both look disastrous. But the good news is they don't occur in the same Hilbert space. So you could have a problem of a negative energy or a problem of a negative norm, but you never have both. So you only have to deal with either one or the other. And then I'll just give you the answer. When you solve the theory, what you find is that the wave functions aren't normalizable. Therefore, the whole assumption that you're working with a standard normalizable theory is not correct. What you do with that is you have to turn the minus c squared into plus c squared by making this z anti-Hermitian. And that's what Carl Bender and I did. And then the theory is bounded from below, and there are no negative norm states. So that's why these fourth order theories look like they're going to be problematic, because they will always bring you into what would appear to be an Ostrogrodsky problem, but that presupposes that these are regular Hermitian operators. But then you have to check. So you construct the Hilbert space, you construct the wave functions, and then you discover that the wave functions aren't normalizable. But that means you can't integrate by parts, and therefore the operators were never Hermitian in the first place. And so that basically is the point that had been missed before my work with Carl on this subject. Okay.
Actually,
that was all I wanted to say.
Is a question from Manuel Asorey from here.
Can you hear me? No. Thank you very much. Can you hear me now?
Yes, very good.
So, I mean, with this method, you arrange the problem, but the question is this solution stable under interactions? So, for instance, if you add a quartic term to this Hamiltonian, is this scheme stable?
Yes. Is that Ilya?
Sorry?
Who is asking the question?
Manuel Asorey.
Okay, yes. The answer to your question is yes, that everything's fine. I've written a paper on this. I've worked out the Feynman rules for loop diagrams. Now, the statement that's straightforward is this. If you found a Hilbert space where all the states had a positive norm, then in perturbation theory, that cannot change. You can't change the norm of states in perturbation theory. So there's never going to be a negative norm problem. What there might be, and this I had to work on, and this is a very hard question, is with this propagator, you will have a cut that would look like it has a negative discontinuity. And that, if that were to happen, then that would violate unitarity. And that's the challenge for radiative corrections. We did actually add on to 3.6 a lambda phi 4. Now, it turns out that when you solve the full theory, there is a second contribution coming from the tree graph. And that tree graph cancels the negative discontinuity. And so the answer is yes. Once you've got the Hilbert space, the fluctuations are going to be well behaved, but they're much more subtle. And the way unitarity works is very different than in the normal case.
Thank you.
Sorry, Philip, just one comment related also then to Latham's talk. I think that in your quantization restriction, you also need to introduce a new type of inner product, right? So you cannot just do the bracket, you need to do the left-right inner product.
Let me answer that slightly differently. The answer is yes. We use a different inner product, but the reason is this. The Schrödinger equation, H psi equals E psi, only specifies the ket. It doesn't specify the bra. So you have a choice in which bra to choose, and can you find one which is such that you then get a positive definite probability? Now, it turns out that in these PT theories, the answer is either it's the PT, the bra is either the PT conjugate of the ket, or in more general case, the CPT conjugate of the ket. However, there's an alternate way to describe it, which you just mentioned, is you can think of a Hamiltonian acting to the right or to the left. And the general statement is the norm is the overlap of the left bra with the right ket. Now, in the Dirac Hermitian case, the left bra is the Hermitian conjugate of the right bra, but that's not general. And that's a very special case, where a Hamiltonian happens to be Hermitian. But the more general case is you should take the left eigenstates of the Hamiltonian and the right eigenstates of the Hamiltonian and look at their overlap. And of course, they're automatically going to be unitary, because one goes like e to the IHT and the other goes like e to the minus IHT.
Yeah, so my comment. Yeah, indeed. So basically, just to continue on the question that I asked to Latham at the end of the talk. Basically, I was asking, it's nice that you can cancel the anomaly, but of course, you need to pay some price. So you need to introduce this higher order derivative term. And then, of course, in principle, you would have stochastic instability. So what you do, you need to quantize, you need to introduce a new quantization prescription. Let's, for instance, follow your approach. If we follow your approach, we need to somehow introduce a new type of inner product. So this means that even when we compute an expectation value, a quantum expectation value, we cannot do the standard bracket, we should do something different. So even if you want to compute the expectation value of the trace of the stress energy tensor, we should even revise that computation, because maybe the expectation value of the trace of the stress energy tensor cannot even be computed with the standard bracket. Okay, so depending on the quantization prescription, maybe one should also then think of how one computes some expectation value. Okay, so that was my point. So that's why you cancel an anomaly, but then if you want to make sense of stochastic stability and so on, one should maybe even revise from the beginning the computation of the expectation value of the trace, depending on which kind of quantization prescription you adopt. Okay, that was, let's say, the question comment. Yeah.
So, okay, I can say that, yeah, sure, your observations are right, but I think that if you buy this assumption, which is typically taken that, for example, a trace anomaly is one who is proportional to the beta function, then you can relate them to things. So, okay, so this does say that if I know how to compute the beta function, then I know the trace anomaly. And this is typically what was done. I think that this doesn't really depend on prescription how you define bracket. This relation that the trace anomaly is expressed via beta functions. We also hold that.
I'm having trouble hearing the. I can hear it a little bit, but not as clear. There was a previous person in the room who I think somehow managed to be more audible.
Would the last speaker possibly get the microphone? I don't know.
Yeah. So, well, I don't know if we may do this. So the last speaker was not last comment was not clear on Zoom.
What you said was, I'm sure what you said was clear, but we couldn't hear it.
Yeah.
Sure, the physics was clear.
Maybe repeat that.
Okay, so I was just saying that I think that at least for the trace anomaly, there is still a relation between this expectation value of the trace of the energy momentum tensor and the beta function, at least at one loop. So I would guess that no matter which way you should compute the expectation value, still is probably related to the beta function. So if you know how to compute the one with beta functions, this should give you the answer also for the trace anomaly.
Sure, I agree with that. I was just saying, in principle, the way you compute a bracket.
Yeah, but I mean that the trace of the energy momentum tensor is a very special operator. And it has expression via beta functions. If you take a very other generic operator, typically you are right that you have to recompute because the bra is different, the cat is different, and so on and so on.
No, look, but you're gonna sandwich this operator with something different, so maybe something can change.
Yeah.
So yeah, sorry,
I'd like to make another comment on the same topic. Forget everything you ever heard about PT, forget about left, right, forget about different scalar product, inner products. Just look at the path integral. You just do, you're integrating over classical paths, and those classical paths look like they have an Ostrogradsky instability, and that path integral doesn't exist, it blows up. That's where you stand. How do you get around that? The answer is you continue the domain of the measure of the path integral into the complex plane. And that's what Carl and I did. And when you do that, you'll find, if the theory makes sense, there will be some domain in the complex plane where the path integral exists. If there's no domain anywhere, then it's just not a theory. Once you've done that, you can then ask, well, now what are the quantum Green's functions that will give me the same answer? And then you discover that there are these funny inner products where the bra is not the Hermitian conjugate of the ket. And that's because you had to leave the real axis to continue the measure, the path integral measure into the complex plane. So the two go hand in hand. You don't have to do something different. The whole issue is, is there a domain where the path integral exists? And the answer is, for these fourth order theories, there is. It's just not one with real fields. That's the surprise.
Latham, you have your hand.
Yes, this is going back a little bit in the conversation now, but I was interested to hear Philip say that I wasn't aware of this paper where you computed the work to higher order and perturbation theory. I was interested, did you do, I mean, there are these extra phenomena that occur in the case where the two frequencies in Pi-Uhlenbeck become equal to each other and the sort of size of the Hilbert space collapses. Do you know, does that change the story at all? Did you do it in that case too, or
It changes the story completely. The paper that I published on interactions was for 1 over k squared minus m1 squared minus 1 over k squared minus n2 squared. Mm-hmm. In the language of Pi-Uhlenbeck, the unequal frequency case. I have not done the calculation that way for the equal frequency because it's just the 1 over k to the 4 propagator. Now, the problem with the 1 over k to the 4 propagator, which is the fourth order, is it's very well behaved in the ultraviolet, but it's problematic in the infrared. However, in the vertices of the loop diagrams, there are extra powers of the momenta because the interaction is a derivative interaction and they keep the theory infrared finite. But I haven't done any explicit calculations. But the answer to your question is, it's completely different than unequal frequency. Now, let me try to answer it in a different way. In the fourth order theory, where you have just 1 over k to the 4, it turns out the Hamiltonian is not merely not Hermitian, it's also not diagonalizable. And this goes back to what's called Jordan block. And when it's not diagonalizable, it means that the Hamiltonian doesn't have a complete set of eigenstates. Now, without a complete set of eigenstates, you can't do scattering the standard way because the unitarity of the S matrix depends on the states being complete. So all of the standard discussion, Landau-Kutkowski cutting rules and so on, don't apply if the Hamiltonian is not diagonalizable. But something else happens. And you could have asked, maybe if I can do another screen share, is that allowed? I don't want to give a whole talk.
Go ahead, just.
Yes, all right. Maybe I'm still the host, still a host. There it is, okay. I'll see if I have it here.
Let me just say we have, while Philip is looking for his slide, which please go ahead. Okay, we have 5 minutes yet until we need to close the session because people locally will go to a sort of refreshment drinks before reconvene tomorrow. So please go ahead, Philip.
Okay, this is where I calculated the loops. And what you see is the S matrix becomes not right-right, but right-left. And so that's the general S matrix. But there's a problem. And the problem is what happens when you have equal frequency. And Latham mentioned it this morning, the probability suddenly becomes 0 and everything becomes 0 norm. And now the question is, where did the other state go? Let me see if I have it here. I thought I had it. Well, I don't have it here. I don't see it. So let me just state it. What happens is when you have all the two frequencies are the same, then the second state becomes linear in T. it becomes non-stationary. So you lose an eigenstate, but the Hilbert space of the theory remains the same, and therefore you gain a non-stationary state. Now, the set of stationary plus non-stationary is still complete. And what Carl and I showed was that you had to use both of them in order to get unitary time evolution. So that, and that's the way that it works. Sorry that I can't find it because it was nice. Well, never mind. Never mind. Don't worry about that. So that's the answer. Is you have non-stationary states as well, and between them and the stationary, you still have a complete basis. But you can't construct a regular S matrix.
I wonder. Oh, sorry.
I see Shravan has raised his hand, and please, a final question, if we may, and then we close. Please, Shravan.
Okay, my question is about a bit different subject. So I would like to ask Artem Starodubtsev if he's around.
It's there. It's in the room.
Okay. Okay.
Yeah, he's there.
Hi, Alexei. My question is basically, how do we understand that? Well, what is the real observational imprint for stochastic inflation? How do we test it?
Well, in the standard case, where is no observational imprint of stochastic inflation, just because it works in the case of smooth inflation potentials, it results, it's better to say, stochastic inflation effects results work only if perturbations, scalar perturbations are large. So just from the fact that the observed fluctuations are small, it means that with stochastic effects of stochastic inflation are actually small. I cannot say now how exactly they are small, but they are certainly small. Another case which is discussed in the literature now, in particular, that David Vance just had e-papers on this topic with Vincent Benin. So if slow withdrawal conditions are broken, and this is the how we can get large perturbations at the end of inflation. So in this case, there is no, as far as I understand, there are no general agreement. So I was also think that stochastic inflation effects will be small even in this case. But once more, it's not where I'm not insisting that it's the final word. Maybe David can add something on this topic. So may stochastic inflation effects be noticeable in case of when we have breaking of floor roll approximations at near the end of inflation.
Thank you. You say something, Shravan?
Yeah, well, I don't know if David wants to comment this. Otherwise, I want to ask a question.
Just one very brief. I already got signal.
Okay.
A smoke sign.
Okay. So
from afar to close this.
Final question: what is the open problem which we don't understand about inflationary quantum fluctuations?
Whoa.
This is a very general question, but I really want to know your expert answer on this.
Well, I would say I don't see any problem in principle. The only important thing is, once more, if simplest inflationary scenarios are sufficient, and in this case we don't expect a large number of primordial black holes or peaks in the primordial gravitational radiations at small scales, at scales much less than like cosmological ones, or indeed such features exist, and the simple answer that in this case we should introduce some additional parameters, at least two parameters into any model, even not specifically inflationary. So one parameter showing the scale of for this where these large peaks are located, and the second parameter is the amplitude. Okay, so once more, at present, since we don't know neither that there exist primordial black holes and some peaks significantly higher than the standard predictions of the inflationary scenario for gravitational waves. So at least at present, we don't see anything a quantity from observations, but once more, okay, expecting of possible discoveries, we should be prepared for it, and that's why we indeed many people, including myself, worked on more complicated scenarios in which these large perturbations, both scalar and tensor, are possible.
Well, thank you so much. And
can I just? I know you want to wrap up, Paolo. But,
no. I'm okay. I got a signal that they are going to a reception for a drink. So you are the one that are preventing it.
Well, just to give people something to discuss over drink.
Go ahead.
I was wondering whether it would be fair to say that we are still interested in perhaps in whether there's sensitivity in our inflationary calculations to say to UV completion of the theory, or indeed changes to the underlying fundamental theories. I mean, like Alexei, I'm very comfortable using our sort of low energy in effect description or semi-classical descriptions of field fluctuations, but I wonder if we should be at least mindful of the fact that perhaps, I mean, whether we can explore through the fluctuations, the UV completion, even perhaps, the high energy regimes of the theory beyond those that we think we imagine we study in the, of course, this is going beyond the usual perturbative approach. Right.
Okay. I would also like to make a comment to this David comment, and just the point is, okay, we have predictions for inflationary fluctuations, but this does not mean that these metric perturbations are really fundamental field. We use it and use rather effectively, but it may well appear that the correct field for which we really would have UV completeness is much more complicated. And just actually, it was just one example which I presented in my talk that really we can speak in usual language about different, well, at least in the simplest model of inflationary scenario. So we can speak about difference in duration state, in the difference in the duration of inflationary stage, well, very close to the Planck time. But that this occurs because we are speaking not about exact net perturbations. We are in fact speaking about averaged netting fluctuations, averaged over actually large scale. So, and what's more, the example of gravitational waves which are really measured showed that we can use average quantities even in the regime that the real physics is completely different. So once more, speaking about scales of the order of 10 to minus 18 centimeters, speaking about the measurement in gravitational wave, and we need that remember that actually at energies 10 of order of 100 TeV are actually at least energies that physics that there are no protons and neutrons were quark and gluons, and that's why so the usage once more I repeat, we present our inflationary results for inflationary perturbations actually not for real netting perturbations, but for the average over actually scales much exceeding the Planck scale. So that's why the question of UV completeness, maybe the answer is that to find the UV complete figure, that we should consider a different quantity, more fundamental quantity, which reduces to usual metric perturbations only after averaging.
Very interesting and challenging as well as enthusing. So it's already 5 to 6 p.m. local time. I know that they are committed to the reception with some soft drinks and other drinks. I don't know. I'm not there. So let's close, and we will reconvene tomorrow at 10:30 continental European time or 9:30 local time, and other times depending where you are. I will be sort of teaching most of the day, but not all the day, so I will be popping in. And let's just thank all the speakers and thank all the contributors, and also for this second in a series, I think, if I'm not mistaken, conference, very interesting, that get people from all around the world to join a common interest and pursue. So thank you very much, and now over to Sravan or Lucas so that they can close the meeting.
Yeah, well, as you said, we will meet again tomorrow at 10:30 Central European time. So
thank you very much, Paolo.
No worries, my pleasure. See you.
See you tomorrow. Bye bye.
See you tomorrow. See you tomorrow, everybody.
Tomorrow.
Bye, everybody.
Bye, everyone.